So we're supposedly live.
Exciting.
I will maybe see if I can pull it up on YouTube and check. Okay, we are live. Cool. All right, so I guess it's time to get started. So welcome to those of you watching to the Catalyst.jl workshop. Before we get started, I just wanted to mention that we're going to be going through some Pluto notebooks we put together, kind of presenting to you some features of Catalyst, and they're all up on the web. So I just wanted to show you very briefly how you could get them and load them in case you want to actually have the code running while you watch. So let me share my web browser, hopefully. So if you go to the Catalyst.jl website, which I need to make that font a lot bigger. So you can just Google Catalyst.jl. There is a link in the README that both to the Pigeonhole where you can go if you want to ask questions. And there's also a link to where we've posted our Pluto notebooks. And so this is the repo that has our notebooks. And what you want to do if you want to actually load them and follow along using them live is you want to just download this. You can download it as a zip file, save it somewhere on your computer, and navigate to whatever folder wherever you saved that. In my case, I've got it saved. Let me show you where I've got it saved. Well, I'll leave it up. Navigate to wherever you've got it saved and start Julia there. And then within Julia, when you're within the root folder that has this project.toml and manifest.toml in it, just load the using package, activate it, instantiate it. Now you may wait a little while because it's going to pull down and load all the packages and compile them. Run Pluto, and basically that'll pull up your web browser. And at that point, you can start navigating into the tutorial folder and opening the various tutorials that we're going to go through. So that's a way you can kind of follow along, and hopefully that works for everyone. It should be self-contained as long as you make sure to run these commands in the root folder where the manifest and project are located. So, okay, so with that said, let's start the workshop. So let me just open back up my presentation. Okay, so like I said, we're going to tell you about Catalyst.jl today. Maybe Torkel, maybe you could post in the Pigeonhole the link to just the Catalyst website to get the stuff for people coming in late.
Yep, I'll do that.
Okay, thank you. I'm Sam Isaacson, and Torkel is my co-presenter here with me today. We're two of the developers for Catalyst.jl. Chris Rakakis has also done a lot of development on it. In fact, he created the original version of it, which was DiffyQ-Bio way back in the day. I believe it was Chris. Maybe it was Chris and Torkel. And a lot of people have helped out with adding features like Yingbo and Shashi and some others. So I just wanted to mention them and mention that we've got several sponsors for SciML and Catalyst via Chan Zuckerberg and Welcome, and people supporting us on GitHub. And so we very much appreciate all that support. It's allowed me to do a lot more work on it this year during my sabbatical, and hopefully future support will let us keep working on these kinds of projects. So we're mainly going to be going through Pluto networks to show you how to do stuff in Catalyst today, but I wanted to give you maybe a 8 or 9 minute overview of kind of what Catalyst is and how we're going to use it before we get into actually kind of going through the details. So Catalyst.jl is a modeling toolkit-based symbolic representation for chemical reaction systems. So it creates something called the reaction system, which stores a symbolic representation of chemical reaction networks. It also includes a domain-specific language for kind of concisely entering reaction systems into Julia. And then from that language, these symbolic reaction systems are produced. And so here I've got a little example that probably looks complicated, but we'll be going through much simpler ones and building up to this today of the repressilator and how you could type it into Catalyst. And then on the right, there's just a little graph that Catalyst can, for example, generate that shows the reaction complex network associated with this reaction system. These are the kinds of things that we can input into Catalyst and we want to study with it. So one of Catalyst's main features is that it can take your symbolic reaction system and convert it into symbolic modeling toolkit reaction rate equation ODE systems, or symbolic chemical Langevin SDE systems in Modeling Toolkit, or symbolic jump systems that represent stochastic chemical kinetics models and allow you to then simulate those reaction rate equation ODEs or that jump process very easily. And again, we'll show you how to do this very shortly. So that's one of its main, most useful features, is just specifying very easily your reaction system and then generating and solving the corresponding mathematical model. But Catalyst also has a bunch of extra features than just that. So we have a pretty comprehensive API at this point that lets you do things like network analysis. So if you want to calculate stoichiometry matrices or linkage classes of your network, or the deficiency of your network, or whether your network is reversible or weakly reversible. We have functionality for that. One cool thing, which hopefully we will have time to show you later today, is that Catalyst can detect and eliminate conservation laws from networks. So that's a way you can reduce the size of system and, say, make Jacobians of systems non-singular. And that's something we'll come back to. Catalyst lets you do compositional modeling, where you can, say, specify a model for a gene, a model for another gene, and then compose them together into a larger model for a gene network. It also lets you do more than just chemical reaction modeling. You can couple your chemical reaction models to constraint ODEs or algebraic equations, and I'll show you some examples of that later today. And more recently, we've added the ability to have parametric stoichiometry, which lets us do things like have bursty chemical reactions. Catalyst also, by design, is meant to be able to compose well with other Julia and SciML libraries so that you can use it to do sensitivity analysis of your network, or optimization, or parameter estimation, and also so you can incorporate other types of models into Catalyst, be it surrogate models or machine learning-based models, or plug Catalyst into those workflows itself. So what are we actually going to go through today? And this is my last slide before we'll actually start showing you kind of how Catalyst works at the Julia level, at the code level. The first kind of portion of our workshop is going to be kind of an introduction to Catalyst. How do we build ODE, SDE, jump process models? How do we use this domain-specific language to enter the models in? What's Catalyst actually doing under the hood when you take one of these DSL models and then just solve ODEs with it? Kind of what's the process that's going on there? And give you some guidance about how you can, say, optimize simulations to some degree, how you can add extra features in, like calculating Jacobians of ODE models, or making sure that you're using the most optimized jump process simulation algorithm, stochastic simulation algorithm for your particular model. So that's kind of the first portion, maybe the first half of our workshop. And then the second part, we have a bunch of stuff, which maybe we'll get through it all and maybe we won't, that kind of goes into some of the more advanced features of Catalyst. And these include things like how you can model bursty reactions by having parametric stoichiometry that lets you, say, have a random variable as a stoichiometric coefficient, how we can combine multiple reaction models together, reaction system models, into larger ones, how we can add constraint ODEs or algebraic equations with the specific example that I'll show you today of how to build a Hodgkin-Huxley neuron model. Torkel will show us about how we can combine Catalyst with Bifurcation Kit to look at bifurcation analysis of chemical reaction networks, and how we can combine it with homotopy continuation to find all the steady states of a mass action reaction system. And then if there's time at the end, I want to show you a little bit about how we can do conservation law analysis to reduce a network to make it more amenable for use with tools like Bifurcation Kit or homotopy continuation. Okay, so that was kind of the quick and dirty kind of introduction to today's presentation. And I think Torkel is taking over now, right? So.
Yeah. So I will try to share my slides and sorry. Oh. Okay. Yeah, checking that people can see this. And if you can't say anything, just someone warn me before I get too deep into the presentation. So the idea, like what I want to do, is just having a very brief introduction of how to make a simulation using Catalyst model. So really, like, the main part of the package is that you create your biochemical reaction network model and then create a simulation. And we're going to have like more advanced tutorials on how to do that later on. And there will be like a big section actually creating the models. But since this is the main feature of the package, I feel I just want to show this off directly in the beginning so you know where we're getting at. So the first step, if you want to do, is you actually want to create your model. And the main way, or like there are few ways to do it, but one is to use this @reaction network macro. And this is something which Catalyst implements, which is a DSL, a domain specific.
Sorry to interrupt. Just so you know, you weren't sharing the slides. I just shared them for you.
Okay. Excellent.
Now they're removed. Now they're removed.
Okay. Okay. Yeah. Okay. Yeah. I see. We'll try to make another try. Can you see them now?
You haven't shared. They're not.
Oh wait,
added.
no. Yeah, I remember. Yeah. Add them to the window. Yeah, exactly. Add to stream. Okay,
Perfect.
Excellent. Now it should work. Yeah. There was a step to the streaming platform which I forgot about. Okay. So basically, the first step is create your model. We have a few different ways to do this, and we'll go through in more detail.
And
One
Carlo,
is that
sorry,
you use.
I'm gonna. It's a little small, so I'm gonna just go put it on full screen. Is that okay?
Yeah.
Okay. All right. I won't.
No, that sounds good. That means that no one can see me, right? Which might be a good thing anyway.
Correct. Sorry.
I will try to not make any important gestures. Okay. Can people see my cursor, by the way? I probably should check this before.
Yes.
Excellent. Okay. So there's like really two main ways to create a model. And one is to use this domain-specific language. And the second one, Sam will go through more in detail afterwards. And here I will focus on just you create your model using the @reaction network macro, and then you just list all of the reaction events you have in your system. So here I create a normal birth-death process, which is that you have a single species of the system X. This could be, for example, a chemical species, but it could also be, if you model, say, a population dynamics, some kind of animal. And then you say, like, we have a birth process where you go from nothing. So you have the 0 denotes the empty set, to you get one species X, and this happens at some rate B. And then you have a death event where you go from having X to having nothing, and this happens at rate D. And then I create this simple birth-death process model, and I save it in the variable BD model. And next, what we can do is that we can do mainly 3 different types of simulations. So we can make these ordinary differential equation simulations. And typically, this is a good approximation to make when concentrations of your species are very high. So you don't have to care about stochastic effects. And really what you then have to do, you just have to specify the basics. So you have to specify some kind of initial condition. Where do we wish to start the simulation? You have to specify a time span. So at which time period we want to simulate, here from 0 to 50. And then we have to set the parameter values of our model. And here we have 2 parameters. We have B and we have D, so the birth rate and death rate. And then you bundle all of this up into an ODE problem. So the model, the initial condition, the time span, and the parameter value. And then you can solve it using the solve command. And then you plot your solution here. So all kinds of simulations we do using the differential equations package. And I think probably a fair amount of you are very familiar with this. And the syntax to simulating using a Catalyst model and using a normal function using differential equations is pretty much the same. So here we just have our BD model instead of having the differential equation function. Next, what you can do if you have to account for stochastic effects, you can use stochastic differential equation simulations. And this use the chemical Langevin approximation if you want to be technical about it. But in essence, it adds natural noise to the system. And here the only difference is instead of creating an ODE problem, we create an SD problem. And then we can solve it and we can plot it. And we see we get something similar, but we have these fluctuations to the system. So here we smoothly go from the initial condition to a steady state. And here we see we get this noisy solution instead. And finally, what you might have at some points is that you make a jump process simulation or Gillespie simulation. And here we actually keep track on the exact number of X species in our system. So here again, we set an initial condition, and we note that one difference here is that we're going to have an integer number X. So if you look here previously, 2 slides back, I had 1.0, so this is a float because we have continuous concentration. But here we want to track the integer number of how many X molecules do we have in the system. And then instead we're going to use we create a discrete problem. It's just the same. Then we set a jump problem, and then we can simulate it. And then we can see here how the amount of X species in the system kind of evolves in these discrete jumps, we'll go from 1 to 3 to 4. There are probably 2 jumps here in very close proximity. And Sam will go through all of the details, how to make these jump simulations later on. And this is really like the essence in Catalyst, is that you create your model and then you simulate it with whatever approach is appropriate for your application. And now I'll go to the next part of the presentation. And here I will really go into detail of this DSL, so the domain-specific language, where you're allowed to create models using this macro thing. And there are really two, like, as I said, there are 2 main ways to create your models. Either you would use this DSL, where you can use these nice notations, but as Sam will show, you can also programmatically create, so you like specify directly the reaction events. And the advantage with that is that you have a little bit more control over your model, and maybe you want to do modifications of it. And this is really more advantage if you quick and dirty, you just want to get your system model as quickly as possible. And then this allows you to very quickly create a model and then have access to a lot of different simulations. So again, you want to declare that you want to use this DSL with the @reaction network macro. So the macro then allows you to use custom codes in Julia. And then you have the begin end block. And here you're going to have on each line, you're going to have 1 reaction event.
Torkel, did you switch to a new window but not update the stream, because it's still showing your first presentation?
Very good, very good. Let's see here. So, oh yeah, no, went. Yeah, okay. I think I know what happens. It's good that Sam keeps track on things here. So I have to probably stop the screen, and then I'm gonna share the screen. Application. Oh yeah, now I can do it like this. Okay. And then I'm gonna add it up there.
I added it for you. It's up.
Excellent. Okay. Can you see things now?
Yes, all good.
So there shouldn't be too many more transitions. So hopefully we won't have too much of these technical problems anymore. Okay. So fortunately, we're just on the first slide of the next set of presentations. But this is really where I want to go through, like this DSL, this macro, and how to use these chemical reaction notations to create your models. And as I said, here, the model object, you just say the variable in which you want to save your model. @reaction networks declares that here something funny is going to happen. And then you have this begin end block. And here on each line, you can have 1 reaction event. And each reaction event takes a set of species and turns them into a different set of species. And this could, for example, be, I mean, in this case, we have a simple production event where 0 denotes nothing, and here we get an X. And for example, if you're modeling chemistry, you might have a binding event. We have 2 molecules binding to each other, forming a new molecule. If you're modeling population dynamics, you might have a birth event. We have 1 rabbit which got birth to another rabbit, or more complicated, you actually have 2 rabbits giving birth to 1 rabbit. Or if you're modeling an epidemic, so you could model disease spread. You can have an infected individual meets a healthy individual on one side, and the other side you have 2 infected individuals. And then here B, which is the rate that this happens. For example, here you have a birth rate from turning nothing to X, and here we have the death rate. So this is the same model I used for example last one. And here we see that the model can get displayed using this nice chemical reaction notation as well, which looks quite similar here. So I have a birth reaction and a death reaction to create a single species X. And then there's this package LaTeXify, which you can use to take this model and then display the differential equation. So here we have the ordinary differential equation for the rate of change in X we get using this model. And we see a constant production B. And then we have death rate, which is this D rate times the concentration of X. So slightly more advanced, of course. In previous, I only had one species here, or nothing, but you can have several species. For example, here we have Dimerization Model, where we have 2 X molecules which bind at some binding rate and form as a single molecule X2. And then we have the association event where this X2 molecule turns into 2X. And here you can see that I simply add this coefficient before 2 to denote that the 2X molecule that participates in this event. And we can see here this reaction that we have 2X binds forming X squared 2, and then we have the dissociation where we get 2X again. And here again we can display the ordinary differential equations. And here we get slightly different things that happens. And I think Sam will actually go through very much how this is calculated. But the important thing here you see that if you look at the previous one here, we see that if we have nothing here, the rate is just this constant. If we have 1x here, we get the concentration of x times d. So this makes sense. If we have twice as many individuals, I expect to see twice as many death events within every time unit. Now here instead we have 2x molecules and not 1, and then we see the rate of this reactions. We see how many X molecule gets removed is actually X squared times the binding rate. So we can see that the rate of change in X is X squared times the binding rate. And then we have plus this thing where we have the concentration of X2 times KD, so the rate of the dissociation reaction, and then times 2, because each of these reaction events, you're not producing only 1 X molecule, but 2 X molecules. And then the perceptive automator said that actually, like here in each binding event, you actually lose 2 X molecules, should be at 2 here, so that minus 2 X squared KB, which is the case, but there's also a half. So in principle, we have something X squared, you have to account for this extra coefficient, which is basically 1 divided by 2 faculty, which becomes 1, 2. And here I have a slightly more artificial example, just to show that I can have several different species in one. So I have 2 X molecules and 3 Y molecules, and then I just write 2X plus 3Y, and then here I produce a single Z. And then we can see the rate here for the production of Z is that, okay, so we have the rate R, we have the X to the power of 2, because we're 2 X molecules, times Y to the power of 3, and then this coefficients becomes 1 divided by 3 times 2 times 1, so 3 faculty. This symbol. And then, so 1 divided by 6 times, sorry, no, lost. 1 divided by 6 times 1 divided by 2, so it becomes 1 divided by 12. But yeah, in principle, you never actually have to see these equations. So one nice thing for Catalyst is that you just write what reaction events you have, and then the equations are generated. You can look at what you want, but you never have to actually deal with them as you simulate your model. And especially if you're looking at stochastic differential equations or jump, this is a great relief because the noise terms gets quite extensive. And this is really like the base of using the macro or the DSL. And one main feature of having this DSL is just that it should be as simple to use as possible. And you want to use it when you want to create a model as quickly as possible and effortlessly. And to do this, we have a couple of extra features just to simplify notation. And I'm just now going to show off these ones. So one, for example, we created this birthday model, but we see here actually we have one single reaction going 2 ways. So we go from nothing to X, but we also go from X to nothing. So we have B turn 0 to X and D rate turn X to 0. And we can actually simplify this. So here we turn 0 to X, but we have this arrow to show that it's a reversible reaction. So we have forward rate 0 to X and a backward rate to backward reaction X to 0. And then we have to use this tuple thing to show the reaction rate, where the first element here is the forward rate. So B, birth parameter, we go from nothing to X, and D, death rate, we go from X to 0. And I should probably also note that after you have this end command here, what you would do is you list all of the parameters. And this helps the system figure out which symbols here are parameters and which are species. And we'll get to why this is important later on. And then we can check if these models are the same. And yes, they are. So declaring the model like this or like this doesn't really matter. And I should add here, and this is a little bit very tangential, but here I add an additional argument between @reaction network and begin, and this kind of sets the name of the model. And the reason I do this is that I just want these two to have different names to the like true command. But if you want, you can like have different names here. And this is really a parenthesis, but I'm saying this because some people might see that I have this extra argument here, and I won't do that later on. Another thing you can do is that you can bundle reactions that are very similar. So say, for example, here I have a birth-death process where I produce both on species X and a species Y, and then they both degrade as well. So this is just the birth-death model, but 2 instances. And we can see here that I have 2 very similar birth events and 2 very similar death events. And I can set, again, by using tuples here, so I have a single rate B. Both reactions have the same substrate, so like the initial, you start with nothing, and then they go to X and Y. And by using this tuple here, I denote that I want to split this in different directions. So this thing here becomes identical to this thing here. In the same way, I can bundle up the degradation events using this tuple. So here I'm going to have 2 reactions. Both reactions are going to have the same rate, the same product, but input the substrates. There are 2 alternatives. One is X and one is Y. So here this reaction gets split into this one. And especially with degradation events, when I make my own model, I will notice I might have like 7 different species in my system, and they're all going to degrade at the same rate. So they're going to have 1, and that's going to save me having 7 different lines for the degradation reactions. I can just write 1 like this. And this makes models look a lot cleaner. Yeah. So yeah, we see these are just, oh yeah. So another thing you can do is, here these 2 reactions are only different in the product. But maybe I have here cases where I have 2 birth reactions and they also have different rates. So 1 rate birth X and 1 rate birth Y for the 2 birth events. And again, I can like create a bundling here where I say I'm going to have 2 different reactions with 2 different birth rates, BX and BY. The reaction is going to have the same substrate input and 2 different products. And then this is going to pick this rate, this substrate, this product for 1 reaction, creating this one, and then this rate, this substrate, and this product, creating the second reaction. And then again, I'm going to have the same bundling of the degradation events. Now, it's also possible, here we note that this is also a reversible reaction. And we can see that here, I just have 1 reaction this way and 1 reaction that way. And I can bundle even further. So here I have a reversible reaction. We go from nothing to X or Y, but we also go the other way. And then I have to layer or nest my tuples. So here I'm going to have the forward rate, and we can see that that in turn is a tuple because there are 2 different rates. And then we have a backward rate like that. And I think maybe it's probably better to declare your model this way. So like one thing, like it's nice to save a line of code, but I think one thing that's really nice with the DSL is that it allows you to write code where you can look at the code and it's very easy to see what kind of model you have. And if you start to like bundle things and to be too efficient with space, it starts to get difficult to see what actually happens. And I think maybe in this case, this is the level of model which is easy to like see what's going on. But it's up to the user. If you want to bundle things up very much, you can do it. And next, so it's very general what you're going to put in your reaction rate. So the rate of a reaction scales linearly, whatever you put here. And previously, I've just used one parameter of system B or D. But you can be very general what you put here. So here I try putting B divided by D. So you can have some expression of several parameters. You can just have a constant, for example, 1 here. You can also have functions. So maybe I declare a function birth of B is equal to B squared. I'm not sure why I would do this, but I can. And then set birth of B here, model. And then I can see actually like now we get the same def rate, but the birth rate is going to be B squared. And I think like even people have been able to like, you can put a neural network here and stuff. So this is very, very general. One thing which you probably want to use is you can have species concentrations here. So it's quite common that, for example, the rate at which a reaction occurs not only depends on a parameter, but on species of the system. So, for example, one case would be if you have population growth. So then you would have, don't have constant production of rabbits, but the number of rabbits you produce depends on how many rabbits you already have. And then you might get something like here that I go from nothing to 1x, for example, 1 rabbit. And the rate is going to be the amount of the species x. And then like the def might also depend. I mean, I already said like, so if I have twice as many individuals, expect twice as many def events. But the rate that you die might also depend on the population. For example, you might have a carrying capacity. So there's lots and lots of rabbits. There's lots of competition for the food. And then you expect the death rate to increase. So I have death rate times the amount of rabbits. And then we check this model. We're going to see that we get production of X, which is equal to number of X, linear production, and then with this quadratic depth term. And this is the logistic growth model, which some of you might be familiar with. Now, I'm interested in biochemical reaction network, and one common example you have here is that you have some kind of catalyst, which also happen to be where the name of the package come from. And what a catalyst does is that you have some kind of reaction, and this makes the reaction much easier to do. And I think the motivation behind the name is that catalyst makes modeling much easier. So here we see we have some substrate, which is timed to some product, and the rate depends on a parameter k, but also on some species C. And now here comes slightly important detail is that if I were to display the equations of this system, well, we can see that the rate at which S disappear, of course, is equal to the amount of S, the amount of the catalyst, and this constant K, and with the same production rate P here. However, because I have not listed C as a parameter at the end, so the only parameter I've said, only K is a parameter, everything else here is a species. So even though C is not part of a reaction like this, the catalyst is going to say that this is going to be a species. And here I see that I have this thing here where we have dc dt is equal to 0. So you're going to have a species, but this is never going to change. So this is going to be constant all of the time, which might be a consideration. Now, maybe a more natural way to write this is going to say that, okay, the catalyst is part of the reaction, C, is a part of the reaction which is neither consumed nor degraded. So we have a reaction occurring rate K, which takes S and C and turn it to P plus C. And here we can note, so this is a different way to write the same system. We can see we get exactly the same equations here. Now, one thing you might want to do is to say that actually, if C is going to be 0 all of the time, it's never going to change. Maybe I set this as a parameter of the system. So then I can list C here, and I display the equations, and I see that C here is not a function of time, and C never changes. It's not a variable of the system. And one thing this might be note, one error I might do every once in a while, especially with a lot of parameters, that you forget to list a parameter here. So here I have a two-state model. We go from a state X to a state Y, back and forth, iterate Kx and Ky, but I forget to list Ky among the parameters. And then we see that, okay, I forgot the equation here, oh yeah, here you see. So here you see that we actually got another species, Ky. So here we're going to have, even though I think I have a system with 2 parameters and 2 variables, I'm going to have a system with 3 variables and 1 parameter. And this is probably going to generate an error down the line when I try to do simulations. Now, one thing which might be interesting, and Sam is going to go through this later on, that if you use the more advanced, so if you don't keep using the DSL, but mess a little bit modeling toolkit stuff of things, you're actually able to like figure out how can I designate whenever the things in my system is a species or a variable or a parameter. It might actually make sense that you want C to be a species, but if you're then very concerned with computational performance, maybe you don't want to, like, even if nothing happens here, it might make things a little bit slower if the system try to like calculate C rate of change in every time step, even though nothing happens. And it's possible to specify this later on. But this is the kind of things that you want to do. Maybe you don't want to use this DSL type notation. So I said before, I model biochemistry, and one very common function here is the Michaelis-Menten function. And this is typically something you see when you have saturation. So say, for example, if you have a production event and you produce some protein, and the production of the proteins is activated by a transcription factor. And if you have something like here, you can see that if the catalyst, if C goes towards infinity, well, this rate goes towards infinity. However, what you have is you always have some kind of saturation. So when you want to produce a protein, well, you have limited amount of, for example, DNA. There's only one gene typically for the protein. You have limited amount of ribosomes. So even if you have an infinite amount of the activator, you have a maximum rate at which you can produce your protein. And here, I'm going to have a simple self-activation model. And one reason is we're actually going to get back to this later when we do some simulation stuff, where production will go from nothing to producing X. And we have the def again. But instead of like before having a constant birth rate, I'm going to say the production of X actually depends on activator. And the activator is going to be X itself. And then I use this Michaelis-Menten function, which is X divided by X plus K. And then multiply by some V, so maximum production rate. And then we can see we get this equation where we have Vx divided by K plus X minus this constant thing. Now, one thing this is interesting, actually, we have already implemented because this is a function we imagine occurs quite a lot. So if you just do mm of X Vk, and then you would get this same function. So here you have this function can just be written like this, and then Catalyst know that, oh, you want a Michaelis-Menten function. And in the same way, there's the Michaelis-Menten function, actually a special case of the so-called Hill function, and the Hill function base x the exponent n to x, k, and x here. So we're going to have, instead of having x, we have x to the power of n, x to the power of n, k to the power n. And if set n is equal to 1, we're just going to get the Michaelis-Menten function. And again, we can then just write Hill, k, v, x, v, k, n. And we get this one. And currently, these two are the only like functions which are already implemented. But we think those are the most common one people will want to use. And another thing you can use is you can have time here. So the symbol T designate the time of the systems, like how long you are in the simulation. And again, if you just write, for example, b divided by t, so you have a birth-death model, but I just say that the rate of birth is going to be reduced with the time of the system. So as we go very far into the simulation, the birth rate is going to be very small. And then we can see that we get this b divided by t, and this is going to work perfectly fine. And one way you can do this, and this is a slightly convoluted way to write it, but this you can basically make a birthing where you have birth times some function here, which is basically going to be a step function. So before time t node, this thing is going to be 0, and after t node, this is going to be b. And then you can have a simulation where nothing happens in the beginning, and then sometime t node, suddenly the birth kicks on, and the system starts happening. And one reason I'm writing this one here is actually I don't recommend to use this approach. So there's something which is called callbacks, which people familiar with differential equations might be familiar with. And this is basically a way to implement events. And this is a clearer and cleaner way to do this. In addition, when this is going to create a discontinuity in the system, so you're going to have some point in time where you go from having 0 rate to rate b, and this might also create problems for numerical solvers. So you can do like this, but you probably don't want to do it like this. And then I just want to show off this thing, because one thing which is nice with Julia is that you can use Unicode characters in your code. So for example, here we have, I never really showed you, but you can do a backwards arrow. So you can do an event k x, something like this. I have no idea why you actually want to do this, but this is possible. But in principle, all different arrows can be used instead of. So if this here looks nicer, you can write it like this instead of like that. And especially if you use something like VS Code, it's quite easy to get. You just do that left, right arrow, and you can autocomplete, and you get something like this. And I mean, it's dependent on taste. I think in this case, using this is probably just as good. But you can also, for example, use Greek letter symbols. So one thing, I'm working on something called bacterial sigma factors. And all sigma factors, they're called something like sigma v. And if I can't use Unicode characters, I would have to write my sigma something like this, which works. But I can actually use my sigma v here in the model. So here a production reaction will go for nothing. And here again, you can use the empty set symbol instead of 0. This is quite equivalent, but it's a matter of taste. And here I can write sigma, and I can even use some superscript. So here I write sigma v. And in this case, I think this actually helped me, because it's easier for me to look at the model and see, okay, this is sigma v. And if I show it to my experimentalist colleague, it's also like a little bit nicer. And here, for example, I can write v node using subscript 0. And again, like this doesn't matter awfully much, but I think it's nice that you can do these kind of things. And yeah, then I have like a final thing here that you can bypass the law of mass action. So really, the law of mass action is what we use to calculate the rate at which a reaction occur. So for example, we said that this reaction occurred at rate P1, but for example, if you have def event, you're then going to have P2 times the concentration of X. And if you have, for example, a binding event, so you have two things, you're going to have times the concentration of both things. And I think you almost always want to have this, but say that you in the DSL want to disable this and just really customize at which rate this occur, you can use this type of arrow. So I have like unfilled arrow like this, and then we're going to have, I have like different 5 different reactions where we have 5 different things, and we'll create species Y1 to Y5. And here we can see that production rate of Y1, 2, 3, 4, 5 is just going to be P1, P2, P4, P5, independently of what we write here. And I think like 99% of the time you don't really want to do this. But sometimes you have someone that have like a model where it's mostly a biochemical reaction network model, but there's something strange going on somewhere, and they want to like customize that one. And then this allows you to do that. I think if you end up using these kind of things for all of your reactions, you might, maybe there's like a different modeling package instead of Catalyst you should look at. But if you want to add some funny things, this is possible. And this is just by giving the user the options to say what I want and not want. And here, like another like small thing. So say like I create a model, here create a binding model where we have production degradation of two components X and Y. So we produce X and Y, they degrade, and then we can bind and form a single complex XY. And then if I want to investigate my model objects, like you usually just input binding model to whatever methods you want whenever you simulate or something else. But if you want to have a look, then you can do species of your model, and you get a list of the species of the system. You can do parameters, and you get a list of parameters. And if you do reactions, you get a list of reactions. And if you were to like look into there's like a few different more fields in reactions in order the reaction system. So in binding model here, but I think these ones are probably the main ones you might be interested in. And then like at the end of most notebooks, we're going to have like, so this is the end of this segment, and I'm going to hand over to Sam, but I'm going to say that in the end of most of the bigger notebooks, there are going to be a set of exercises. You might have some breaks, and this can be some like useful thing if you want to work yourself with. So yeah. And so here, if you open this notebook in Pluto in the end, you can see like here's some quite simple exercises to do. And with that, I think I'm going to hand over to Sam for the next section.
All right. Thank you, Torkel. So I think since we're already maybe a little behind schedule, that let's just keep going, and maybe we can plan a break halfway through. I think that might be the best way to do it. So I'm going to share this, and hopefully I can add it to the stream. Okay, cool. So what I wanted to go through is a little bit about what's going on under the hood. So we just saw a really nice overview of kind of all the power of the DSL from Torkel and how you can use it to implement type in and enter chemical reaction networks in a bunch of different ways, and a bunch of different notations, and adding different functions for rate laws and such to it. But what's going on under the hood when you then take that and you call ODE problem on it to simulate it, or you call SDE problem to simulate it, like he showed at the beginning. And we'll show more about simulation right after this section, but I wanted to show you kind of what's going on under the hood a little bit before we then go and show you about the simulations. So basically, I wanted to make sure everybody knows what is when we create an ODE and simulate an ODE model with Catalyst, what's the ODE model? What's the jump process model? What's the SDE model? Tell you a little bit about how it relates to Modeling Toolkit, and how, if you don't like the way we're building chemical rate laws, how you can modulate that with this combinatoric rate laws option. Okay, so here, let's look at what happens like with an abstract just ODE model that we build via Catalyst, okay? So here's kind of the most general way I could write a mass action type of reaction. I have species S1 to SL, and I have M1 of S1 as a substrate, and M2 of S2, and so on and so forth. And I make N1 of S1, N2 of S2. This is my general reaction. What does this actually give me when I generate ODEs with Catalyst, okay? Well, if I call nu sub I the change in species I, so it's the product stoichiometry minus the substrate stoichiometry, this is the change in the ith species due to the reaction. And what Catalyst assumes is that the ODE term this reaction generates is that stoichiometry coefficient times the rate of the reaction times a rate law that has this form. It's the product of the species amounts to the substrate stoichiometries divided by this factorial term. And the reason that I wanted to show you this is to make so that everybody could see this, because sometimes when people are doing ODE modeling with reaction networks, they don't want to have this factorial. Their rate already has it built in. So I'll show you in a little bit how you could get rid of it. So this is the term that would appear in the ODE for the nth species from this one reaction. And then you can generate other ones analogously. And this would correspond to basically typing in a reaction like this, modulo, I put ... instead of typing all the abstract terms. So that's kind of what an ODE that comes out actually is when you run this. So one question, though, is we're talking about Catalyst as a symbolic modeling system that is a symbolic model for a reaction system, and it uses Modeling Toolkit for the ODE systems or the jump systems or SCDs. How can we actually get at those? And so I wanted to kind of just show you quickly how you could get at that. So Catalyst reaction systems that you generate via the DSL, like here, can be converted into ODEs or nonlinear equations or steady state equations or SDEs or jump process systems. And these are all types of Modeling Toolkit abstract systems. And so when you type this in, what you're doing is creating a symbolic reaction system. RN is a reaction system in Julia. And that is a type of Modeling Toolkit abstract system. And so really, one could also just directly type in the reaction system. And we'll show you how to do that a little later when we're doing some fancier applications. Then we need to specify, of course, like we saw earlier, our initial condition mapping. So this says initially I have 1x, 1y, 1z. Initially, I set my rate to be 1. I set the time interval I want to solve on to be 0 to 10. And then I create a differential equations.jl ODE problem from my reaction system. Okay, and that's what I can now solve using differential equations. But under the hood, this is doing a lot of work. When you call ODE problem, it's taking your reaction system here, and it's generating a symbolic set of ODEs, and then it's calling ODE problem on those in Modeling Toolkit. And so you can actually do that yourself if you want more flexibility. So here I'm converting the Catalyst reaction system into an ODE system by calling convert. And you see that gives us our ODEs symbolically. You could have in Modeling Toolkit actually just type these ODEs in yourself directly as using Symbolics.jl variables to type them in. And we'll see some examples of that a little later, how to type in ODEs directly. And so this is the kind of symbolic equations that are stored in the ODE system. And of course, here you see those combinatorial factors that I pointed out in the rate law. And at that point, we can kind of, instead of solving and simulating the ODE, creating an ODE problem from the reaction network, we could equivalently take this symbolic ODE system and make an ODE problem and simulate that, which is what Catalyst is doing under the hood. So first, I take my mappings from symbols to numbers for the initial condition in the parameter, and I have to put them in a form that Modeling Toolkit can use. And Modeling Toolkit always works with Symbolics.jl symbolic variables. So I have to convert this Julia symbol into a symbolic variable. And that's what this function here does. It's just converting them over. And then I can, taking the symbolic ODE system and the converted initial conditions in parameters, I can create an ODE problem from that. And if I go and now solve my two different ODE problems, on the left, I've got the ODE problem coming directly from our reaction network. On the right, I've got the ODE problem where I took our reaction network, I converted into a symbolic ODE system, and then I made an ODE problem from that. And sure enough, we get the same answer with both of them. So this gives us a little insight into what's going on under the hood. We're converting our reaction systems into Modeling Toolkit symbolic ODE systems. And that's a place where you can possibly perturb the system later on if you want to modify the ODEs or such. And we'll see a little more about that, like I said, when I talk about Hodgkin-Huxley. So, okay. So as an aside, I mentioned that our normal rate laws divide in that reaction that I had up here. This generated this rate law, this term in the ODE. But I said, what if you don't want the factorial? What if your rate constant's already got that built in, which many people often have? How can I generate it? Well, it's actually very easy. When you create an ODE problem, you just pass a keyword argument called combinatoric rate laws, and you set it to false. And then that gets rid of these combinatorial factors. If I convert to an ODE system before making an ODE problem, I can pass combinatoric rate laws into that. And now my symbolic ODE system also no longer has those factorial terms appearing. It just has the stoichiometry, right? I'm losing 2x, 3y, and gaining 4z for this reaction. So that's a way I can disable and slightly change the rate law depending on how I want to interpret my rate constants. Like this here is what we had previously, and then this was the version without the combinatoric rate laws. And sure enough, if we solve the version where we create an ODE problem from a reaction system, or we solve the version where we create it from converting to an ODE system and then creating an ODE problem, again, we get the same answer. So the punchline is there's kind of two things. We can always create things by passing our reaction system from the DSL into the ODE problem or SDE problem, or we can take it and convert it to symbolic ODEs and then pass that into ODE problem. And if we want to disable these combinatoric scalings, we can just use this combinatoric rate laws argument either to ODE problem when we're creating that from a reaction system directly, or into ODE system when we're converting our reaction system into a symbolic system of ODEs. Okay, so far we've talked a lot about ODEs. I just wanted to mention very briefly, and then I think we're then going to show you some pictures and how we actually do some simulations for some different models. What are the actual equations that we're getting when we have SDEs, chemical Langevin equations, or jump processes? So if this is the reaction again, this is the ODE we said Catalyst makes by default, where this term here, the K times the product, is the rate law of the reaction. Well, this is the corresponding chemical Langevin equation SDE model that the reaction would generate in Catalyst. So this is how the Lth species is impacted by this reaction. You'll notice there's a drift term that's exactly the same as the ODE's term. So that's the same. But then there's a noise term where this is a Brownian motion that gets multiplied by the square root of the rate law times the stoichiometry, the corresponding net stoichiometry coefficient. Okay, so this is your classical chemical Langevin equation. And when you make an SDE system from a reaction network or an SDE problem, this is what Catalyst is internally generating for you. If you're interested in Gillespie methods or stochastic chemical kinetics, you have this type of equation that comes up. This is what's called the time change representation. And so this is a jump process where the amount of species, the Lth species, is changing according to a unit Poisson counting process whose time is evaluated based on the integral of this function A. So basically here, nu L is how much this species changes when the reaction occurs. It's the net stoichiometry. And Y is counting how many times the reaction occurs. So when Y has the value 5, the reaction has occurred 5 times, and you change SL by 5 times the amount the reaction changes it. And what sets the rate or the intensity or the transition rate of our jump process is this, what's called the propensity function, A of S1 to SL. And what Catalyst assumes is that your propensity function has the following form. It's K times the product of SI minus 1, down to SI minus the substrate coefficient plus 1 over MI factorial. So maybe it's worth typing in. So for example, if you had 2A goes to 0, I'll just write this as a comment, then what you would get is something like, for that rate law, you would have K times A minus 1 over 2. So that's what the rate law, or the probability per time that the reaction would occur in Catalyst, would be for the jump process. And just like sometimes you don't want these factorials and you use this combinatoric rate law to get rid of them for ODEs, you can pass the same argument when you're creating SDE problems from a reaction system or an SDE system from a reaction system to get rid of the factorial terms here if you don't want them. So just to kind of show you that, here's how we would create an SDE problem for the chemical Langevin equation directly from our reaction network. And then you can pass in the combinatoric rate laws. If it's true, that would keep those factorial terms. Here's how we convert it to a symbolic modeling toolkit SDE system. And then we create an SDE problem we can solve from that. And then here's how we do a jump process model. If we want to go directly from the reaction system, we create a discrete problem to tell differential equations.jl that our process is evolving in jumps. It's not changing continuously in time. And then we say that the type of discrete jump problem we have is a jump problem. And here we pass in this extra argument to tell it how do we want to actually choose what reaction occurs and the time they occur. And we'll talk more about that later, but this, for those of you who have seen these models before, this is what's called Gillespie's direct method. So this is saying use Gillespie's direct method to sample which reaction occurs and what time the reaction occurs at. But a completely equivalent way to do that would be to convert our reaction system into a Modeling Toolkit symbolic jump system, and then make a discrete problem from that and a jump problem from that. So there's always this workflow option of going directly from the reaction system or going via the model, the symbolic mathematical model that you want to use. And we'll exploit that in some of the applications that we're going to show in the second part of the tutorial, the kind of second half of the tutorial. And I think that was everything I had for this part. So I think now Torkel is going to take over and tell us a little bit, actually show us some examples of actually doing some simulations. Since we've kind of shown you a lot, maybe abstract, it's time to start showing you some actual using Catalyst. And you're muted right now, Torkel.
Being muted seems inconvenient. Okay. Hopefully everything should be in place now. Okay. So this section is really like simulating Catalyst models. And I will go through like a few different, like how you do various types of simulation things. For example, if you want to do like Monte Carlo simulations and just like the basic syntax. And I think this is all going to use, so I said already, you have differential equations.jl. This package, which probably is one of the most well-known Julia packages, but if you're here and not a Julia person, I should just say like, this is the tool we use for all simulations. And there are probably going to be a few people in the audience who are very well familiar with how to use that package. And you're going to see a lot of things you're familiar with. So first, we're going to just start with, again, declaring the model. Here, like I hinted a little bit before, we're going to have this positive feedback model. And this has some nice properties, so we can see some cool thing in simulations. And here we basically have a single species X, which gets produced and which get degraded. We have linear degradation, so it just disappear. And then we have the production. It's a Hill function of X. And that means that the rate of X production is going to increase the more X we have. So I have this positive feedback that if we get increased production in X, well, we're going to have more X. If we have more X, the rate of X production increase. And then that kind of goes on. And we have a couple of parameters. We're not going to pay very much note to it, but I have this parameter I, which stands for input. And I kind of like here, we have the activating term in the Hill function, which is X and I. And the beginning, I was going to say I is 1, so I have a constant input, but I'm going to do some things with this one later. So I'm just going to flag that already now. Okay, but now we use Catalyst, so I've created a positive feedback model. And now we're just going to simulate it. So the first thing, I've already showed this before, you're an ordinary differential equation simulation. And first we declare our initial condition. And here we have a vector. In the vector, we're going to list all our species. And we use this pair way to like say that the initial condition of species X is going to be 5.0. Okay, here we're only one species, so there's only one here. Next to time span, typically you're going to start from 0, but you could start from some other time point. Sometimes I do simulations where something is going to happen, and then maybe I say like this activation, this happening event happens at time 0, but I do my simulation from an earlier time point. So you could actually have like a simulation that starts at time -10. And then it goes on for 100 time units. And then I'm going to set my parameter values, and I use the same notation here for the initial condition. I list my parameters in a vector, and for each of them, I say which value they have. And then, okay, now we have everything I know for my model. From the simulation, I have a model, an initial condition, how long I simulate it, and my parameter values. And then I just call the solve command on my ordinary differential equation problem. I get a solution object and a plot object, and here I can see. So I will see that we start in the initial condition from 5 X molecules, or a concentration of 5, and then with time we go to this steady state, slightly over concentration 11. If we look at the solve command, previously, so my first presentation, I only had a single here, the ordinary differential equation problem, but here I actually give this Rosenbrock 23 argument, and this designates which numerical solver you use. So if you don't set any one, differential equations will just auto pick one, which they think is good, but you can also set which one you want to use yourself. And for small, simple models, I always found this Rosenbrock 23 solver is very good. But if you really want performance, like there are people that know very, very well which solver to use, and if you go to differential equation, you can see there's tons and tons of different solvers. And here just showing that if you want to like change the properties of this plot command, there's tons and tons of options to use. For example, here I can set my the X label to time, Y label concentration here. I really like to have this frame style box where I have a box around the plot instead of just having two axes. LV stands for line width, so I can make this line thicker. Here label it equal to nothing. I can remove this label. And if you go to the plots package, so it's just plots.jl and then check attributes, and you can find tons of these options. So I'm not going to discuss that any further, but it's very much possible. And then again, if we want to use these chemical Langevin equations to make a stochastic differential equation simulation, again, I'm just going to say I create an SDE problem instead of an ODE problem. And then again, I call the solve command. For stochastic differential equations, I have to use different set of solvers. Quite often, I just use this implicit EM, which stands for implicit Euler-Maruyama solver to solve my SDD stuff. And then again, use the plot command. But the only difference here, I said I want an SDE problem. And then Catalyst will say, okay, we're going to use the chemical Langevin approximation implementation of noise, as Sam showed previously. And here I'm just going to show like the first additional feature. So say that I kind of want to see like how noise affects this simulation, and I see here we get this like nice transition, and here we see that the noise kind of like the amount of noise you can't really see how like we're approaching new steady state. So maybe I want to tune the amount of noise in the system. And here I'm going to declare a new model, positive feedback noise scaling. And the only difference is going to add an additional parameter here, eta. And this is because I want to tune the amount of noise or tie the amount of noise to this eta parameter. Okay, so what I do then, of course, I have an additional parameter. Eta, I want to have to set this to a value, going to set 0.1. And then when I create my SDE problem, I'm just going to add additional option argument, noise scaling is equal to, and then I use this thing here, which is modeling toolkit type notation. And I won't really go into detail much here, but just if you're interested in scaling noise, I would just copy something like this in the beginning and then maybe learn what this actually means. But here I declare a parameter eta, which is the same one here. And then I solve it and plot it. And then we see we got a lot less noise than we got here. And here just linearly scale the noise term, which Sam showed before, with its eta parameter, which is 0.1. I'm not saying that this is always a good idea. The like amount of noise for these reactions should be for eta is equal to 1, but there might be a situation where it's convenient to like see what happens. What I often see if I have someone else have implemented an ODE model. I want to see what happens, what have a noise here. And if I directly use the chemical Langevin equation, I just get a noisy mess. something like that. And then I say, okay, I'm just going to like add a little bit noise and then slowly scale up the noise and see what happens as I approach at is equal to 1. And then you can use this noise scaling option. And next, what happens if I use a lot of noise? So if noise here set is equal to 6.0, and we see we get this quite immense fluctuations. And this is a rather artificial example, but I also want to show that if I run this again, yeah, so sometimes I might get this error where I get blah, 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 aborting. Model specification, the solution is unstable. And sometimes what happens is that because differential equations automatically use adaptive time stepping. And if you get a lot of things happen really fast, it might think the solution is unstable and you're going to halt it before you reach the final time. And here we can see we only reach about 9 time units. And one way around this is that you can actually disable the adaptive time stepping. So here I'm going to use the same thing, click add parameter, create an SDE problem and solve it. But then to the solution, I'm going to add an argument adaptive is equal to false. So I'm going to turn off the adaptive time stepping and then set the t is equal to this. And then I'm just going to take a fixed time steps and just make time step every 0.001. And then we see we can actually solve this without problem. And then again, now we see if you use this, I need to have very small dt. So here we're going to save every 0.001 time unit. So in total, we're going to save 100 times 0.01. We might get a very dense solution. And one additional argument that might be useful here is to have this save at, which means that I'm just going to use dt is equal to 0.01, but I'm not going to save it at every time, every 1,000 time unit. I'm just going to save it every 10th time unit because I don't need to save that much and it clogs up memory. So really this combination of arguments can be good if you have this problem. Now, if I actually were to look at this solution, we can see we add so much noise that we quite often here have negative concentration. Of course, we can't have negative species concentration X. So something bad is going on here. And one way you can make some kind of callback, I'm not showing this today, but there are ways to force you to be in a positive domain. But quite often I say that if you are encountering that you go into the negative domain, you probably should not use an SDE problem. So then for very high noise or very low species concentration, the assumptions of the chemical Langevin equations we use to implement SDE equations break down. And then you should use Gillespie's approach to make these jump simulations, which Sam will go into more detail later on. And this is a thing yeah, you can solve it here, but if you have this negative species concentration, you probably should use this approach instead. And here, so I mentioned callbacks earlier when I discussed time. So quite often what I look at biochemical system, we have some input and kind of you have a system which is in a steady state, not much happen, and then you add something and then the system activate. And there you want to implement at a certain time something happens. So some kind of event. And if you go to differential equations and search for callbacks, this is basically how events are handled. And there are a lot of different options and certain already implemented. And I'm just going to here show a very simple callback. So this is going to be a so-called preset time callback, which say at some time point, something happens. And I create this activation callback in this case by calling preset time of 2 arguments. The first is the time points when this happens. And here I'm going to say at time point 20, something will happen. And this is the effect function, which is going to change the state of the simulator. And this takes 1 argument, an integrator. And again, if you search for integrator DFAQ, you can find exactly how this object looks like. And here I'm just going to very simply say that you take the integrator, you take the P field, P, and you take the first argument, So here this is the first parameter, and the first parameter we can see when you create a model is going to be this I. I'm going to take the first one, and I'm going to set this equal to 3. And then, okay, I want to simulate. I set my parameters. It's going to be the same before, but this input argument is going to be 0. I'm going to make my SDE problem. Briefly ignore this deep copy thing. I will explain this later on why this is important. And then here I set this optional argument. Callback is equal to activation CB. And here I actually have these arguments, the adaptive. I think there might just be a remainder from when I use it. But anyway, and this is going to say this here. And then we can see that before time 20, the solution kind of are around this 10, which is about similar as it was before. So here it's like 10, 15. But then we can see around time 20 something happens when this callback kicks in and increase the input argument 3. And we see that concentrations start rising, and when they reach like a final concentration of X around 100. And then we can see probably like this system had 2 different steady states. We have one steady state here for low concentration X and one for high concentration X. And here switching this input moves us into this high state. And this you can use using these callbacks. Now, we see here that this is a very noisy thing. And often what you have if you simulate something with noise, you want to make similar simulations to like see what different outcomes can we get. So here, for example, you want to make Monte Carlo simulation. And here I've simulated the same system 15 times. And of course, one way to do this is that you just simulate, run this one time, you run it a total of 15 times, saves all of the solutions and plot them together. But there's an easy way to do it. And that's creating an ensemble problem. So the start is going to be very similar. I have the same parameters. I create the same SD problem. And then I want to create an ensemble problem where I basically take my SDE problem and pass that to a solve and say like I want to solve this several times. And then you need an additional, you have something called a problem function. And this problem function is going to take your problem, and I is going to say, so basically, no, I'm going to take from this end. So when I create my ensemble solution, I'm going to solve my ensemble problem, and I'm just going to use, select which SD solver I want to use. I'm going to give it the callback again. So I want to use the same callback, but I'm going to give this trajectories 15, which basically say like, I want to solve my SD problems 15 times. And I'm going to plot the solution, and here we got the 15 trajectories. Now, this problem function is not going to do much now. It basically going to take your problem and your SD problem and apply this function to the problem at the beginning of every simulation. And this is important that, say, for example, if you want to do an ensemble solution, but say that you want to simulate an ODE problem for 15 different initial conditions, and then you actually you not want to solve the same problem in every iteration. So here I solve a stochastic problem, want to solve the same problem every time. So the problem function is just going to return the original problem, the SD problem. But you have this I, which is the iteration. So it's going to go between 1 and 15, and then repeat is just going to be these 15 things, which is the total number of repeats. And then you might want to modify your problem here. But if you want to just make an SD Monte Carlo where I solve the same stochastic problem several times, this problem function is just going to be this trivial problem function of this is equal to problem. And there's a small thing we much need to watch out for here. And then if you see, I only add the input at time 20, and you see, for example, this blue simulation looks like previously. But for several of these simulations here, we see that we actually start to activate before 20, so before the callback kick in. And there's a reason for this. and this is slightly technical, but I want to say this because this can cause some problems for people. And what's going to happen here is that I solved my problem the first time. So I solved my SD problem in my first iteration, and then the callback kicks in at time 20 here, and modify the parameter I to become free. And then I solve it again for the same SD problem using the same parameter set, but in the second simulation, it's just going to use the same parameter set, which was modified by the callback. So this, the remaining 14 times I solve this problem, actually I'm going to start with I is equal to 3. So actually what I have to do here is to make some modification. And here actually I'm going to use this problem function. So I'm going to say in the beginning of every Monte Carlo simulation, I'm going to take my problem and I'm going to call this Remake Function, which basically is a way to modify a differential equation problem. And again, I say P is equal to deep copy. So this is just a copy of the original parameter set. And this is going to say in the beginning of every simulation, I'm going to take my problem and modify it by setting this parameter set. And this ensures, and we can see here, that when I modify the parameter set, I only modify it for this iteration of the Monte Carlo simulation, not all of them. And here we can see all 15 simulations, we go to time point 20, and then they activate nicely. Okay. And this is pretty much Monte Carlo simulations, but I'm just going to show some simple thing. So one thing I like to do when I plot a lot of these simulations, like the plot gets quite messy, you can use this line alpha argument to the plot thing, which kind of fades the line. So if this is 0, they're going to be all transparent, but making them slightly more transparent, I think makes the plot nicer. And you can also use this indexes argument if you only want to plot a subset. So if you go index 1 to 5, and here I will plot the first 5 simulations. And I think I actually missed this, but one important thing here is that this ensemble thing can automatically parallelize your solutions. So if you check it up, there's actually, if you do an ensemble solution, there's actually an additional argument here, which is an ensemble solver. And you, for example, have this solver, which says that, oh, I want to solve this, but I automatically want to parallelize over the threads of my computer. Or I can do ensemble serial, which just naively going to solve one and then the next without any kind of parallelization. And actually, this threads is the automatic selection. So this, in addition to be a nice way to just bundle all of the simulations, automatically allows you to parallelize your solution. And I'm just going to show up some very small features. So in my previous, I only have a single state, but say that I have a 2-state model, so I have a state X and one state X2. And then I make the simulation, I can see these two here. But then if I use the vars argument, then I will only display the second variable. So then I only display X2. So say if you have a large model with maybe 100 species, you probably don't want to show all of your species, and then you can use this to say that it's actually only this one or this few number of species which I want to show the concentration of. And then, of course, if you want to access and do some statistics or want mean concentration or find peaks or something, you can always access, for example, the solution object sol.u returns a vector with the concentration of all the species in every state of the system. And sol.t returns all of the time points. And here's another thing, which a neat thing, because we have this modeling toolkit, is that if I create this model here, I'm going to use a brusselator. Okay, we're very familiar with how to make an ODE simulation. But if I use this Jack is equal to true argument, then I automatically compute the Jacobian of the system. So then here I'm not going to use a Jacobian, but here I can compute a Jacobian for this system and use that to hide the solution. And if I do this sparse is equal to true thing, then I compute a Jacobian and also make it sparse. And this small example doesn't really matter, but I just want to show this thing here. So here we have big model BCR, and I solved it for various simulation length. And here I didn't use the Jacobian. If I say I want to compute the Jacobian, we see that we get a quicker solution. And if I also say I want to be sparse, I get even quicker. And here we say get over 1 order of magnitude speed up by using a sparse Jacobian as opposed to using this case here. So this is kind of like considerations you want to think about, that if you have a very big model, there are ways to really speed up your solution if you need speed. And this is one way we can do it. Yeah, and again, here's going to be an exercise if you want to do it at the end, just to like do some SD simulations. But yeah, this is really the simulation part of the presentation done.
Do you think, should we maybe take a 5-minute break and then I'll come back and talk about jump process simulations? And then we'll go into kind of some higher level applications of everything, I think.
Yes. I think this having the break now is good.
So maybe we'll take a 5-minute break, everybody, and then we will resume in 5 minutes. And I'll put a slide up just so everyone on the stream can see that. So.
Yes.
All right, folks, welcome back. Let me get my sharing set up. Okay. So we just saw from Torkel very nicely how we can, some considerations when we're trying to simulate the ODE or SDE models that we've converted from Catalyst. And like he said, and we probably should have said much clearer up front, we're using Differential Equations.jl to do our ODE, our SDE, and our jump process simulations. So specifically, we're using ordinary diffeq.jl, stochastic diffeq.jl. What I'm going to tell you about now is how we can simulate jump processes using jumpprocesses.jl. So we'll see some Catalyst models, and I want to tell you a little bit about some considerations that come up in questions I've seen people get hung up on when trying to simulate jump process models from Catalyst or even directly with jumpprocesses.jl. So in particular, I'll tell you some considerations about performance tuning. So some of the different solvers you can use, how you can play, or how you can reduce memory use by the solvers, because that can very easily get quite big. And then I'll show you how you can use callbacks, because using callbacks with the jump processes is slightly more work. You have to be a little more aware of what's going on than if you're trying to use callbacks with the normal differential equation solvers. So as kind of my illustrative example, I'm going to work with a model of what's called a toggle switch. So this is two genes. Gene 1 makes mRNA at some rate. The mRNA can degrade. Gene 2 makes mRNA2 at some rate, which can degrade. Each of the mRNAs make their respective proteins. The proteins can degrade. And those proteins can feed back and slow down the mRNA's production. So this says that, notice that these rates that mRNA is getting made here, as the amount of P2 goes to infinity, the rate that M1 gets made gets smaller and smaller, and the same for M2. So these are repressive Hill functions. And so basically, gene 1's protein inhibits gene 2, gene 2's protein inhibits gene 1. And this is a little DSL-based model for it that you can cook up. And if you simulate that, you see a figure that looks like this on a short time scale. And you can see here the jump process nature where the amount of, say, here, M2 is constant, and then finally transcription occurs and you get a new one, and finally transcription occurs and it gets a new one. So you see these kind of long piecewise constant curves that represent the amount, the number of mRNAs and proteins at a given time. And the code for simulating that is right here. We've kind of gone through this before, but just to remind you, we create mappings from the symbols for each parameter or each species to the parameter's value and the species initial value. And notice I'm using integers for the species because this is an exact jump process simulation where I want to know the number of mRNA and the number of proteins. So I can use integers instead of floating point numbers for that. I create a discrete problem like we've seen a few times from our toggle switch. I create a jump problem from that. And again, I'm picking Gillespie's direct method as the way that I'm going to sample which reaction occurs next and which time it occurs at. And in differential equations, in jump processes.jl, we called this an aggregator. So an aggregator is in charge of figuring out which reaction should I execute and when should I execute it. But in addition to giving an aggregator, when I call solve, I have to give a time stepper that reads what's the next reaction, what's the next time, and updates the solution, saves the new solution state, updates the current time in the system. And that's what SSA stepper does. So it's a special time stepping algorithm specifically for these kinds of Gillespie method problems or stochastic chemical kinetics problems that's optimized to be fast for them. And so here's just an example of doing that, and what you can see comes out of it. And so let's start talking a little bit about optimizing that. So if you look at this graph, we're really saving every single jump of the process. And in fact, every time this guy jumps, we have to save two numbers. It saves the state before the reaction occurs, and so it jumps down, and then the state after. And so you can imagine if you have a lot of transitions, a lot of reactions, you start saving an enormous amount of points, and very quickly you're going to destroy your memory, especially if you're trying to use an ensemble problem to run hundreds of thousands of simulations and collect statistics like Torkel was showing before. So what we can do to get around that is, of course, don't save the solution at every single reaction event. Just save it periodically at some fixed times. And so I wanted to just show you how to do that because there's a little bit more one needs to do when you have a jump problem to do that. The first thing you need to do, and here's kind of the code showing it, is when you create your jump problem, you need to set the save positions keyword argument to false, false. Okay, so what this says is don't save the state of my system right before the reaction occurred, and don't save the state right after it occurred, right after you jumped. So by doing that, you'll no longer have a curve that tells you exactly the solution at every point in time, but you won't be saving every single reaction event, the state of the system, which uses up much less memory. Then I couple that within the solve command, telling the solver to only save every 10 seconds or every 10 time units. And putting those two together, I save much less data. And that allows me, in this case, to simulate my system up to time 100,000 time units, which for this toggle switch is kind of cool because what we see is we get this switching where sometimes the system is in the state where there's a lot of P1 and only a little bit of P2, but then the stochastic fluctuations kick me sometimes into a state where I get a lot of P2 and a little P1, and it goes back and forth, flipping back and forth. And just to show you, if I run this, it should be pretty quick. If I run this when I'm not streaming, it's instantaneous. If I run it while I'm streaming, it takes 5 seconds. But as you can see, we run it, and pretty quickly we get a new solution curve, and we see the flip, even though I'm running out to 100,000 seconds. And I do promise you, it is a lot quicker than it appeared there. The streaming is slowing my computer down. So that's one way to control and speed up your simulations, is make sure you're only saving at the times you need to save, and make sure you use this save positions keyword so that it's not saving every single time a reaction occurs when you're simulating your jump process. Now, I was going to tell you a bit about what's in a Modeling Toolkit jump system, but maybe I'll just very, very briefly overview it because I want to save a little time. Basically, when you turn a Catalyst reaction model into a Gillespie method model, into a Modeling Toolkit jump system, there's a decision that has to get made. So Differential equations.jl and jump processes can encode 3 different types of jump processes. There's what's called variable rate jumps, which are very general, and they work for pretty much any type of rate function and state change you want, but they're kind of slow to simulate. There's what's called constant rate jumps, which have some limitations on them, but are much faster to simulate. And then there's an even faster special case called mass action jumps, where if we know our reaction is just a regular mass action reaction with a special rate constant, we can put it in even more optimized form. And so jump processes.jl, its solvers work with these various types of jumps. And the more you can get your system as mass action jumps, the faster your simulations will generally go. And the cool thing about Catalyst is if you want to use jump processes.jl directly by hand, you have to go and say, okay, is this jump a variable rate jump? For example, if you had a rate constant K of t that was time dependent, then you would need to make it a variable rate jump. But Catalyst will automatically bin things into the optimal jump type for you. So you never have to think about that. You just let Catalyst handle all of that. And there's a lot more detail if you want to understand what's going on under the hood in terms of the types of jumps on jump processes.jl, but I think I'm going to leave it at that just for the purposes of this workshop. And instead, what I want to tell you a bit about is what are some of the simulation algorithms that are available for jump processes. And there's basically 8 of them that we've got available. So we haven't quite matched what Chris has developed for ordinary DiffyQ, where there's like 200 methods. But we've got 8 of them, and they offer kind of a trade-off between their performance and the types of systems that they're fastest on, as I'll show you in a minute. So from Catalyst, when you make your jump system and your jump problem, you can use any of these. Some of these require things called dependency graphs that say when a given reaction occurs, it will change these species. Which other reactions have rate laws depending on those species, because we need to recalculate their rate laws after the change. And so there's these things called dependency graphs that if you've ever looked at these stochastic simulation algorithms before, you might have seen. And one typically has to construct them to use the more optimized algorithms. Luckily for us, Catalyst and Modeling Toolkit does all of that for us. And so we can just use any of them right out of the box. We don't have to do any extra building. And there's 8 of them. There's Gillespie's direct method, which is kind of the standard jump process simulation algorithm and is really good for small systems of 3, 4 reactions, maybe even 10. There's the first reaction method, the next reaction method, the sorting direct method, this rejection direct method, the composition rejection direct method, and these 2 rejection SSA methods. And these ones I put in italics are ones that generally are among the best performing ones for given applications, which is kind of what I wanted to show you a bit about. So usually you want to try some subset of these, and one of them will probably be the fastest for your given reaction system. So I wanted to just show you a few examples of different reaction systems and the performance these different solvers come out to show you how it can vary. So I'm using here examples coming from the DiffyQ problem library. So you can load the DiffyQ problem library to load these examples yourself. And the first one that I wanted to look at is just a very simple gene. So this is a Catalyst model for a gene network that's in the problem library. So I haven't typed it out. I'm just loading it in. This is a gene that makes mRNA. The mRNA makes protein. The protein in mRNA can degrade. And the gene can bind to a protein, or a protein can bind to the gene and turn it off, put it into this repressed or turned off state. Okay, so it's a very simple system. It's got 5 species, and it's got 6 reactions. And if I simulate it and kind of look at the median runtime across all those different methods I showed you, and here we're looking at the time relative to direct, then we see that the fastest method is the sorting direct method, which is maybe 85% the runtime of direct. So it's a bit faster. And the rest of the methods are slower than direct. So this is a small system, and that Gillespie's direct method is about the fastest, though you'd get a little bit of a performance boost with this sorting direct method. If we go to a slightly more complicated system, so here now we've got a network that's got, I don't know, maybe about 20 reactions and maybe about 10 species that we took out of this paper by Gupta and Mendez. And this is just a network that's modeling a protein that can be phosphorylated, have different phosphorylation states, and undergo enzymatic reactions in those states. So it has a lot of structure. It's what's called the multi-state model of that paper. And if we go and we take that model and now we load it in and then we run these different solvers on it, we see kind of a different set of benchmarking results. So again, sorting direct is one of the fastest, but this RSSA, this rejection SSA method, is actually a bit faster. And so it actually does a bit better. And they're both a decent amount faster than regular direct, right? They're, I don't know, what is this, 40% faster, 30% faster? Which for a given simulation that only takes, 1/10 of a second, maybe you don't think that's a big deal. But if you want to collect statistics and run 100,000 simulations, that starts adding up. And so using these faster solvers can make your life a lot nicer and better by giving you more speed and reducing the time you're sitting and staring at the computer. And this, just to make a big jump now, Torkel mentioned this B-cell receptor signaling pathway model, which has about 1,000 species and 24,000 reactions. So it's a very big model. And we can load it in using the reaction network importers package. This is a SciML package that can load BioNetGen exported files into Catalyst. So it's a way to get models that are developed in another simulator into Catalyst. And if you go and take a look at that package, there's some examples showing how to use it. We can kind of look at how well the various Catalyst methods do compared to BioNetGen itself, which uses this sorting direct method. And we see the following kind of results. So again, this is simulation runtime in milliseconds, I believe. And then this is the final physical time that we ran the model out to. So we ran it out to 10 to the 4th seconds or 10 to the 5th seconds of model time. And we see that the Catalyst rejection SSA with composition rejection simulation is by far faster than these other methods. In fact, it's almost 2 orders of magnitude faster than the next fastest Catalyst method, and quite a few orders of magnitude faster than BioNetGen's method, which is sorting direct. And so I just wanted to show you these to kind of give you the flavor that very often when people make these jump process Gillespie models, they just automatically use the direct method. It's the simplest. It's definitely, if you have a very, very small system, it's about the fastest. But as soon as your systems start getting bigger and bigger, there's some other methods we've got in there that are very well optimized and can potentially give you much faster jump process simulations. And the kind of basic advice, just to kind of scroll back up, would generally be for a very, very small system, use Gillespie's direct method. If you have a system with maybe 10 to 20 reactions, very often sorting direct will be the fastest. And if you start getting a big system with hundreds or thousands of reactions, Usually the rejection SSA or the rejection SSA with composition rejection are the fastest. If you actually have a spatial structure, so you want to build a model where you have not only reactions between things, but say reactions that correspond to hopping between lattice sites or that correspond to something moving between cells, and you have a lot of cells you're having things transfer between, that kind of structure can often do good with the composition rejection direct method. So sometimes that method can actually give you the best performance. So these ones I've highlighted are kind of, generally I would recommend if you're ever trying to simulate stochastic jump process models via Catalyst, you should play around with a few of these methods, especially if you have at least 10 or more reactions, because you may find much better performance with one of these other ones. Okay, so the other thing I wanted to tell you about jump process simulations is how we can add events into them. So we saw how to do that from Torkel in the SDE case, and I just wanted to show you the analogous thing for jump processes because there's one other consideration that may come up. So the first thing is that when you use this SSA stepper to simulate a jump process algorithm, we only support what in Differential Equations.jl are called discrete events, not continuous events. And that's because the stepper basically assumes the system is constant between reaction events or constant between the events that could occur. So we can't have anything that evolves continuously with SSA stepper. So the way discrete events work, as we saw earlier, is you give a condition, and that condition is checked at the end of every jump of the system for whether it's true. And when it is true, it gets executed. And that condition can be used to change the state of the system or change parameters or terminate a simulation. And so what I want to show you is a couple of different ways to do this. So here, let's go back to the model I showed you a few slides ago of a gene that gets repressed. And let's try to make a discrete callback to stop our simulation the first time our gene gets repressed, gets turned off, and to save that exit time. So we're going to try to do what's called an exit time problem, or a first passage time problem, to calculate the first time that our gene transitions from being available to transcribe to being repressed. And so here's a very simple code for that. I set up my system, my negative gene expression model, so that initially the gene is on. I'll call that state 1. Initially, the GNA is not repressed. I have no protein and I have no mRNA initially. I convert it into a jump system because I'm going to simulate it as a jump process. And then I want to be able to figure out which component of the solution vector corresponds to the repressed state so that I can test when I enter the repressed state. And so the way I'm going to do that is I'm going to take my jump system and I'm going to unpack from it the symbolic variables that Modeling Toolkit stores that correspond to the DNA, the state that you're in, the DNA is unbound, the gene is unbound, and the state that it's repressed. So these are symbolic variables that are used by Modeling Toolkit that represent the repressed state and the unrepressed state. And then what I can do is calculate all the states of my system, which will just be DNA, P, DNAR, and mRNA. I can find which of those states is equal to DNAR in the state vector, and that will tell me in my solution vector the index of that species. Okay? And now I'm ready to make my callback. So first I make a condition. So here, this is the current solution. This is the current time. This is the Differential Equations.jl integrator object that stores the current state of the system along with the past history and all the other information. And then I'm going to pass into it the index of the species that I want to check for, which is the repressed, the index of the DNA being in the repressed state of that state. And then I just say when my solution at that index is 1, that's my condition to activate my callback. And what do I do at that time? Well, I'm going to save the values of the state, and then I'm going to terminate my simulation. So I'm going to tell it as soon as this condition is 1, save the state and terminate it. Okay. I create a discrete callback based on that. And then I create my normal problem just like I would normally do here. So this is just creating the discrete problem from the jump system. I don't need to pass in any initial conditions because I set default values. If you set default values in this way, they're already attached to your system, so you don't need to pass an initial condition. I give a time span vector, and I pass in my reaction rates, which are part of the problem that we loaded from the problem library. I'm just going to simulate it with the direct method. And so I pass back my jump problem and my callback. And then I can call solve. So I call solve with the problem I just created. Here's my problem. Here's my callback. I use the SSA stepper. I don't save the value at the final time because my callback is already saving that for me. So if I saved it here, I'd be saving it a bunch of times. So I don't need to save the last value. And then I pass in my callback. And then if I run my simulation, we see the following. Let me run another just to update it. And so you see here, blue is the state where the gene is available and transcribing, and I'm making mRNA. And then the first time that my gene gets repressed, when the purple jumps up to 1 and the blue, you can't see it, jumps down to 0, that's when my simulation stops. Okay. And so from that, the final time in my solution object will correspond to the exit time that I first entered the repressed state. So I can write a little function to save a whole bunch of exit times in case I want to calculate their statistics, and that's what I did here. So I make a vector. I say if I want to calculate n exit times, I make a vector of length n. I loop through that vector. I solve my system, and I take out the final time in the solution object. So sol.t is the solution vector, as Torkel showed us earlier, and I just pull out the final time in it, and I save that. And that gives me back all the exit times over, in this case, 100,000 simulations. So I get a giant vector of all my 100,000 simulation exit times from running the simulation a bunch. I could also have used a ensemble problem to do this, as Torkel showed us, but I thought it was easier to just make a little function of my own in a loop. And then I can plot a histogram and estimate the PDF of the exit time, and we see the following. And so in that kind of way, we can kind of do a nice calculation and look at the probability density function for how long it takes my system to first become repressed. And so a callback is a very nice way to kind of run your system and stop it when a first passage time problem for a first passage time problem. Okay, so that was the first kind of callback. I wanted to show you one other example of a callback, which is a very, very simple drug treatment model. So let's suppose I have a bunch of, say, cancer cells, and my cancer cells are produced at rate B, and they die at rate D, but they're not dying as fast as I'd like. So what I'm going to do is I want to give a treatment, and what my treatment is going to do is my treatment is going to reduce the birth rate. So every time I give a treatment, I'm going to take the birth rate B and cut it in half, reduce it by 50%. And I'll show you the code for that in a minute. And I'm going to give 5 treatments, and we'll see what happens. Now, the main reason I'm showing you this is that when we modify in a callback our solution, U, or a parameter value, we have to make sure to call reset aggregated jumps. What that does is that tells Gillespie's direct method in jump processes, hey, we changed a parameter or we changed the solution. You need to recalculate the time the next jump occurs and the next rate occurs because we changed some of the properties of the system. If you don't do that, you won't get correct results. So here's what the basic code looks like. Here's my birth-death system. I convert it to a jump system. I want to change the parameter B, the birth rate. So I unpack that symbolic variable from the jump system. And then I search through the parameter vector of the system to figure out the index of the symbolic rate B inside the parameter vector. That's what B index tells me. I set up my initial conditions like normal, again, converting them from the kind of Catalyst way of using symbols into the modeling toolkit way of using symbolic variables via the symmap to varmap function. And now I'm ready to make my callback. So I'm going to use, like Torkel showed earlier, what's called the preset time callback. So I'll set it up so that I give a treatment at time 4, times 6, times 8, times 10, times 12. I just make a vector of those treatment times. And then I make a function for how I want to modify the state when treatment occurs. And all I do there is when I give a treatment, I set the parameter vector that's stored in the integrator. I evaluate it at the index of the birth parameter, and I cut it in half. I multiply it by 0.5. And then this is the key thing I need to remember to do. I tell the integrator to reset the aggregator, to reset the jump process solver, to make sure it knows that I've changed a parameter. I can take my treatment times and my effect function that modifies the parameter and make a preset time callback. I create a discrete problem and a jump problem. One of them I'll pass the callback in, one I won't. So this will have no treatment. This will have treatment. And then I just run my simulation using, again, Gillespie's direct method, and I plot it. And we end up getting these two figures up here. With no treatment, we kind of go to a steady state and fluctuate around. And with treatment at those little orange dots, the parameter that's the birth rate of the cancer cells gets cut in half. And suddenly we see that the amount of cancer cells goes down because they're dying and they're not getting put back into the system at the same rate. So that's kind of a very simple example, but it highlights one caveat or gotcha to be aware of if you want to use these callbacks or events with jump simulations, is to make sure if you're changing the solution value or you're changing a parameter value in your callback that you call reset aggregated jumps. Okay, and I think that was everything that I wanted to say on this one. So let me see. So I think I'm going to go on now, unless any questions have come up. It doesn't look like it, though. This is what I wanted to show, kind of what we wanted to talk a little bit about next is some of the symbolic modeling capabilities. So we wanted to show you maybe some more advanced applications that we can use for building chemical reaction models in various ways. So in particular, how you can build bursty reactions where the amount of proteins that get produced are random. So that'll be parametric stoichiometry. How you can build networks symbolically and programmatically, which can let you build like chains of cells that you hook together, or chains of genes that you hook together. And a little bit about how you can add in constraints like ODEs or algebraic equations to couple into your reaction network model, which I'll illustrate with the classical Hodgkin-Huxley equation for simulating neuronal dynamics. Okay, so far everything we've been doing is via the domain-specific language for Catalyst. So here you see an example of a very simple chemical reaction network model called the originator. And so this is a simple model that oscillates. So here I built it using the DSL, and here I just simulated it using the the same kind of notation that we've seen before, using differential equation.jl sit5 solver. And you see we get an oscillatory chemical reaction network in this case. Now, what I'd like to show you now is another way to build it using the symbolic tooling that's built into Modeling Toolkit and Symbolics.jl, which can give us some more flexibility. So we're going to build the same exact model, but going symbolically instead of via the DSL. And then we'll start to see how that lets us do some other advanced features. So here I'm going to specify my parameters. So I'm creating 5 symbolic parameters for the reaction rates. And here I'm specifying my species amounts and the time variable as variables. So these macros have now created Julia symbolic parameters and Julia symbolic variables that I can manipulate. So for example, and again, this is all built on top of the Julia computer algebra system, Symbolics.jl. So for example, if I take x, I can build a rational function from it, x squared minus 2x plus 1 over x minus 1. And then I can simplify that expression, and it factors it and eliminates the denominator. And then if I want, I could do substitution. So I can say replace x minus 1 with y, and it will substitute it out. So this really shows you that I'm just doing everything on top of the normal computer algebra system that's represented by Symbolics.jl. But for our purposes, we're going to think of the k's as our rates and the x's and the y's as our species variables. And now, using the symbolic interface, we can construct our reactions in the following way. We build Julia. Here, reaction is just a normal Julia structure. Actually, don't remember. I think it's a regular structure, and it's an immutable structure. And we basically just create a reaction with some inputs. So here I specify the rate or the rate expression. This could be K1 times T if I wanted my rate to grow in time. Or it could be K1 times X if I wanted to have another factor of X in the rate. I give a list of the substrates of the reaction and a list of the products of the reaction. And if there are no substrates or no products, I just say nothing. So in this case, the first reaction, I have an X and a Y, and I make nothing. And if you don't, at that point, the assumption is that the substrates and products have stoichiometry coefficients of 1. So all of these get coefficients of 1. If I want to use other stoichiometry coefficients, then I have to give a 5-argument form. So here I have a substrate X with coefficient 1. I have a product X and a product Z with coefficients 2 and 1. And that gives me this third reaction here. And so I make a vector of these 5 reactions. Here you can see how they're represented. And these are now 5 symbolic reactions that we're storing, we've created. And now from those, I can then build a reaction system just like we would build via the DSL. And there's actually a third way to do it that's a hybrid. If you want to still have the nice way of typing reactions that the DSL does, but you want to build these individual reaction objects, because say you're writing a program and you want to build them in a loop or something, you can use the @reaction macro. So this builds just one reaction object instead of a whole reaction system, which is what the reaction network macro builds. So here I built each of my 5 reactions using the same notation that we use in the regular DSL. And you can check by just testing equal that the 2 reaction lists I get are exactly the same in these 2 cases. So I've built these 5 reactions in 2 different ways. And now we're ready to build our system. So now I just create a reaction system passing in my vector of reactions and the time variable, the symbolic time variable. And I'm going to name it originator, just like I did in the DSL. And if I check, remember up here, I created the variable Rn and I named it the network originator. If I check, is Rn equal to the one I just built? Symbolically here, sure enough, they're equal. Okay. And a key thing about the equality is the equality requires that you give them the same name. So when you say @named here, it sets the internal name of the reaction system to the name of the variable you type. If you wanted to give it a different name, you could use the name keyword argument. And I could have said Rn2 equals reaction system RxST name originator. This would make a reaction system with the name originator, but stored in the variable Rn2. But in either case, as long as you give them the same internal name, these will be the same exact systems. Catalyst will check, are all the reactions and species and parameters the same? So this gives us a fully symbolic way to construct our reaction network from a more programmatic interface than using the DSL. So let me show you some of the cool things that enables. And the first is parametric stoichiometry. So suppose I want to have a protein that gets made, that's produced from transcription in random bursts. So there's a rate K that the protein gets produced. And when it's produced, a random amount of them, M, is produced. So M here is a random variable. In particular, M will be a shifted geometric random variable. So it's a geometric random variable whose smallest value is 1. And then our protein can also degrade. Let's see how we can actually build that model symbolically. So here I specify my parameters, and there's 3 parameters. There's the rate that I make the protein. There's the rate the protein degrades away. And then there's a symbolic parameter that I use in my geometric random geometric distribution to set the mean burst size. So I need to know what's the average amount of M that gets produced, and B is going to be our symbolic parameter that we'll use to set that. We have one variable, the P of T. Time is already defined, otherwise I would make T a variable too. And now I want to use, have a way to make M a geometric random variable. The way we'll do that is we'll make it a sample from Distributions.jl's geometric distribution. So here I pull in the geometric distribution, and then I'm going to just set that M is a random number sampled from the geometric distribution with parameter 1 over B, my symbolic parameter that sets the mean, plus 1 because I want it to be a shifted geometric, so it always starts at 1. Unfortunately, if you do this, you're going to get an error. And the error you're going to get is the following. It's going to say you tried to use a non-Boolean num in a Boolean context. And the problem here is that the function geometric of 1 over B, it can't take a symbolic variable as input. The way it's coded, it only works with floating point numbers. So some Julia functions, because of the magic of multiple dispatch, will work with a symbolic variable, others won't. So how can we make it work? Well, luckily for us, Symbolics.jl has a cool feature where you can tell it to register this function. And when you do that, it won't actually ever try to pass the symbolic B into it. Instead, it'll just in your final code replace the symbolic B with the floating point B in your final simulation code. So it handles letting you use the function without ever trying to call it with a symbolic variable. So I do this to basically make it usable. And now I can create a symbolic variable M that just calls the geometric distribution with my symbolic parameter B, or 1 over B, the way that it's defined in distributions.jl, takes a sample, a random sample from it, and adds 1 to that. Okay. So this will be my random variable for the number of proteins that get produced during a given transcription event. And now I can just make my reactions the normal way. So I create a reaction that says from nothing, I make protein at rate K, and the stoichiometry, or the number of proteins I make, is M, is this geometric random variable I defined. And then P can degrade to nothing at rate gamma. I can build a reaction system from that list of reactions in this way. I give it the list of the 2 reactions, I give it the time, and now I've built a reaction system with this bursty production of protein, and I can go and simulate it just like before. So I specify a mapping for the parameters, the values of the rate that I'm making protein, the value of the rate that protein gets degraded, and this parameter B that sets the average burst size of the average number of M that gets produced in a given transcription event. I set my initial condition for the amount of protein I have at time 0, and then just like we've seen a bunch of times at this point, I can go through and simulate it using SSA Stepper and Gillespie's direct method. And I can go through, simulate it, and plot it. And I just wanted to show you there's a few ways we can plot it. So when you go to plot it, if you remember earlier, Torkel showed us how if we know the index of a species, we can plot using its index. But Modeling Toolkit actually allows us to plot using the symbolic variable for the species in a few different ways. So here's one way. I plot my solution that I get. So here I solve it and I return that solution. And I set the variable I want to plot to be my gene network model, my reaction system's P variable, so burstygene.p, and that will plot that specific solution component. So I can use this type of indexing to get at symbolic variables and not have to know their actual index in the solution object or solution vector. And here you see we have kind of a long time where nothing happens, then we get a burst of protein made, a long time, a burst of protein, a degradation, and so on. And we get these kind of bursty production events as time goes on. Another way that we can do it that's completely equivalent is we can take our reaction system, our bursty gene, and we can load the symbolic protein variable P from it using this unpack command. So this just takes the network and says, load into my current environment the symbolic variable P from it. And then I can plot using that, and I get the same exact plot. Finally, if I don't have access to my reaction system that has all the symbolic information, suppose I just have the solution, which doesn't have that symbolic information, I can just create, as long as I know the name, I can create a variable from scratch using the modeling toolkit at variables command, and I can just use that, and it'll still pull out the right one and plot the right one. So in this way, I don't have to try to worry about what's the index of species B in my solution vector, what's the index of parameter alpha in my parameter vector. Instead, I can use the actual symbolic variable for plotting and for accessing the solutions, which is what I'm showing here. So if, for example, I wanted to evaluate the solution at a bunch of times, here I'm making 10 times between 0 and 1, and I wanted to get the value of P at those times, I can just take my solution. So remember, here, bursty solution is the solution, the SSA solution, the Gillespie method solution. I evaluate it at those times, and I tell it the index I want is my symbolic variable P. And I get out this recursive array, diffie-q array. But if I look at u.u, that's the exact solution of my problem at the times I picked, and u.t is the times that I picked. Okay. So in that way, I can use the symbolic variables to do indexing of the solution too, which makes calculations easier. Okay. So that was kind of just a little quick and dirty on how you can use those to kind of plot it. Now, I just showed you how we can make use parametric stoichiometry via the symbolic form to make and simulate bursty reactions. But you might say, yeah, but it's kind of annoying to have to type at parameters, at variables, and type in all these individual reactions. And here's some good news for you. We figured out, and we've got an interface where you can combine the simplicity of the DSL with the symbolic features for just the things you need to do symbolically. And that's what I'm showing here. So here, there's no way in the DSL to create a stoichiometry variable that's a geometric random variable. So I create that symbolically the same way I just did above, but then I just interpolate it into the DSL to use it in the DSL itself. So what this says is basically I'm making my two reactions. 0 goes to m times p, p goes to nothing, and I want to put in for the stoichiometric coefficient of p this symbolic variable m that I previously defined. Okay, so in this way we can kind of very nicely and compactly define the reaction system and just do symbolically the one piece that needs to be done symbolically. And if you check, this gene that I created this way is this reaction network model is completely equivalent to the one that we created earlier, purely symbolically. Sorry about the phone call. That was actually probably my niece wanting to play video games. But this is more fun for me right now. So, okay. So that's kind of an alternative way to build the system. And this kind of interpolation thing works very generally. And if you want to see how to do this more generally, you can look in the Catalyst documentation. But if you want to create a complicated expression for the rate constant, say a function with a lot of stuff, you can define it symbolically. And then, you could define that k is sine of m times, exp of minus m or something. And then in here, you could say $k, and that would interpolate in that expression and use that to define the rate constant of the reaction. And so in that way, you can kind of very nicely combine the two models together, the two approaches together to kind of minimize what you have to type and hopefully make it more readable. Okay, and maybe I'll skip that. Okay. So I had two more things that I wanted to tell you about in terms of the symbolic features. One is called compositional modeling. So it's the ability to define a whole bunch of separate reaction networks and then mix them together. And the application I'll show you in a minute is to build a bunch of genes and hook them together into a gene network that we can simulate. And then I want to show you how we can extend our models with ODEs or algebraic equations that are not coming from chemical reactions to kind of broaden what we can model with Catalyst. So compositional modeling, we have two functions that come from Modeling Toolkit that we can hook into. Extend lets us take two networks and merge them together. And compose, which takes a network and sits it as a subnetwork within another, a subsystem of another. And I just wanted to illustrate this on some very simple examples. So here, suppose I make a network that encodes A plus B goes to C, and I make a second network that encodes C goes to A plus B. If I extend the two together, then I get a new network that has both the reactions in it. Okay, so it's like just merging them together. It's basically like a merge command. And so this is a useful way to define components of a reaction system or reaction network and then kind of compositionally compose them together into bigger networks. Likewise, though, we can also kind of build tree structures where networks are attached to each other hierarchically, and they don't live at the same level. So here, let's build one more network, Rn3, which is my newest reaction network, which is A plus D goes to 2D. So now I've got three networks. I've got Rn1, that's A plus B goes to C, Rn2, which is C goes to A plus B, and Rn3, which is A plus D goes to 2D. And so suppose I take this network and I compose the other two into it. So I take my base network and I compose the other two into it. What this does is it sets them up as subsystems that live below it. Okay, and notice when it shows me the reactions, now they get these names for the network they come from. And the key thing here is that reaction network's 2 C variable is not assumed to be the same as the C variable in the top level network, the composed network, which I call base RN. That was the variable name. In the same way that RN3's reaction network 3's A variable is not the same as the top A variable, is not the same as this A variable. So this is what's called namespacing in Modeling Toolkit. It allows me to have a bunch of networks that I hook together hierarchically, and their variables will be treated as different. If I want them to be treated as the same, I have to do some special things. So in this composed model, I've actually got 1, 2, 3, 4, 5, 6, 7, 8 different species that it encodes. These are all treated as different species. And you can plot these kind of structures using this tree plot command very nicely. And there's lots of ways to manipulate these and deal with these. I haven't really talked about this today, but Modeling Toolkit and Catalyst have lots of API functions for getting at the species and the parameters, and these are called subsystems. So you can get the 2 subsystems out of the composed network by calling the get systems command, and you can look at their name and you see it's RN2 and RN3 like I showed here. And so in this way, you can build these big hierarchical tree structure networks. And I'll show you an example, with, like I said, in a minute with the gene network. But there's an important thing you need to be aware of, though, which is that when you convert your reaction system into ODEs or SDEs or jump processes, Catalyst has to merge these all into one single network. It has to get rid of the hierarchical structure. And that's called flattening. And so there's a command, catalyst.flatten, that gets called when you create ODE problems or ODE systems that merges them all together, but it makes sure to keep the names that indicate what system the variable came from, okay? And so if I look at the species in the flattened network, like I said, there's 8 species, and these include the C's and A's that come from the subsystems. Likewise, if I look at the parameters, I see 3 parameters, including the parameters that came from the subsystems. And if I look at the reactions, I see the reactions that came from the subsystems. They've all been merged together at this point. Okay, so that's kind of the notion or the idea of this compositional modeling, is to build these kind of hierarchies. And you can see this all in a lot more detail in the compositional modeling tutorial of the Catalyst docs. So let's look at an example of the repressilator, which is a gene network of 3 genes, gene 1, gene 2, G3, where gene 1 inhibits gene 2 inhibits gene 3, and gene 3 inhibits gene 1. So they form kind of a circle that inhibit each other. And so I'm going to make a little function here that uses Catalyst to make one gene of the system. The function will take as input the name of that gene and a variable, a symbolic variable corresponding to who's going to repress that gene. So the assumption is going to be that each gene can be repressed via repressive Hill interaction. So this function takes the repressor as input, and then it builds the gene where there's a repressive Hill interaction from that. I'll set some default values for my parameters and a default value for my initial conditions. And then this will return a single gene in my network. And now what I'm going to do is make 3 of these and hook them together to make the repressilator. So the first thing I have to do is I have to specify by hand for the repressor of the first gene, I need to create a variable that corresponds to the repressor of the first gene. So how am I going to do that? Well, I'm going to create this variable which says the repressor of the first gene is going to be the protein that's made by gene 3. Okay, and the plus here is to indicate it comes from gene 3. You can type that, it's Unicode, so you type /_ and then you hit a tab. Oops. At least you should hit a tab. There we go. And that will give you that Unicode plus that lets you indicate that I'm creating a variable from the system gene 3. And then I create gene 1 by calling my repressed gene function and passing in this variable that's the repressed protein from gene 3. And this parent scope says that the way you get access to it says that this variable is not going to live in gene 1 in that network. It's going to be accessible from the parent network that stores gene 1. And we'll see more about that in a minute, okay? Here I make gene 2. And for gene 2, since I've already made gene 1, I can just say g1.p to access its protein and say that's the repressor. And then again, we access that by going up to the parent and then accessing G1 via the parent. And then I make gene 3, by, again, sending in that the repressor is G2's protein, going up to the parent and accessing it in that way. And so now I've got three genes, each repressed by a specific repressor that I chose, and I can hook them together in this way. So I create a reaction system, or I could have used the compose command again. And I say that my reaction system is going to have three subsystems, the first gene, the second gene, and the third gene, which gives me this big set of reactions, okay? And so the way to kind of visualize this is I have my three genes, and my repressolator is a system sitting above them that stores them. And so when I want to get at the repressor for gene 2, I go up to the parent, and then I access g1.p. That's why I had to use the parent scope command. It said, get at that variable by going to the parent system. Okay. And now I can actually go and simulate my whole system. So I have to break the symmetry. In the default values I gave, I set the initial amount of all the protein to 0. So for the ODE model, I break the symmetry by saying gene 1 has 20 proteins initially. I set my time span, I create an ODE problem, and I solve it. I didn't need to set any other initial conditions or parameter values because I set them as defaults earlier up. And sure enough, we see our composed system oscillates, and we get the classical repressolator where gene 1 comes up, and then it starts going down as the next one comes up. I guess gene 1 is in purple, green. So you see as the green gets higher, it starts shutting off the second one. But as the second one gets shut off, the third one goes up and shuts off the first one. And so you get a natural iteration or cycle between the three of them. So, okay. So that was kind of a quick tour of compositional modeling. So the last thing I wanted to show you before Torkel will take back over and show us a bit about bifurcations is how we can add in non-reaction ODEs or algebraic equations. And I wanted to show you this with the classical Hodgkin-Huxley equations. So, of course, Catalyst is great for modeling and simulating chemical reaction systems, but sometimes we have other variables that we want to evolve via ODEs too that are coupled in. Like maybe the volume of my domain should change in time via an ODE. And so I need to write an equation for that. Likewise, I may, for example, when modeling neurons, I may have 3 chemical reactions for the ion channels, but I may also have an ODE for the transmembrane potential, which we'll call V of T. That's the electrical potential across the membrane of my neuron. And so that's the model we're going to build now. So we're going to have 3 basic chemical states corresponding to the 3 ion channels, or I should say corresponding to 2 ion channels, sodium and potassium. And they can flip open or closed. So here M is going to be essentially the fraction of open M-type gating variables. N is the fraction of open N-type. H is the fraction of open H-type. And they flip back and forth from the closed state, which I'll put a prime on, to the open state with the rate alpha S to flip open and beta S to flip closed. So there's an alpha M, that's the rate that you flip from the M prime state where your M channel is inactivated to the open version of it. There's an N prime that represents that the N gating variables are inactivated and they can flip open with the rate alpha N, and so on and so forth. And these rates will depend on the voltage. So as the transmembrane potential changes, these rates will change. So there'll be functions of this other ODE that represents the transmembrane potential. And so in the Catalyst model, I'm going to have 6 variables, M, N, H, M prime, N prime, H prime, for activated and inactivated gating variables that you can flip between. And now here I'm just defining all my transition functions, my probability per time that the channels flip open and closed. So here's alpha M, here's beta M, here's alpha H, here's beta H, and so on, alpha N, beta N. And I'm using, instead of using an if-else statement, I'm using this if-else package. So if the value of this parameter theta is 0, it returns 1. Otherwise, it returns theta over 1 minus e to the theta. The reason I'm using this special if-else command is because that makes these functions work in automatic differentiation. So if we wanted to throw this into higher level applications that needed to use automatic differentiation, having these functions would allow it to work. Actually, it'll work, symbolic differentiation. So it makes it work better from the symbolic perspective. So that's why I'm including these if-else commands. So that's all my rate functions for flipping states. Now I create a symbolic variable that's the voltage, or the transmembrane potential, and I give it this special tag. In Modeling Toolkit, this is called metadata. Okay, so I'm attaching to this the metadata that it is an is BC species is true. So this means that the voltage is going to be considered by Catalyst as what's called a boundary condition species. That's a terminology that comes from SBML, and it just means that V may appear in reaction terms, but we don't generate an ODE from it. So we're going to give it its own equations somewhere else. We're not going to give it any equations from the chemistry. So by setting this, Catalyst knows don't create an equation for it in the chemistry. So now I can create my model for my channels flipping back and forth. And you see it looks a lot like what I wrote above. I say that the rate that I transition from the inactive end state to the active end state is alpha n of V. And I just interpolate in this V variable that I created. And then this is the rate that I transition from the active end state to the inactive state. Okay, so in this way, I've created a Catalyst reaction network that has all my transitions. They look kind of ugly because it's substituting in these functions up here. But it's really just these 6 reactions that I wrote up here using S for those 3. Finally, now we've got all our chemistry defined, but we'd like to attach to this an ODE for how V changes, specifically this ODE. So that we can do by building an ODE system in Modeling Toolkit and adding it to our Catalyst model as a constraint. And so that's what I'm doing here. So I'm going to define a whole bunch of parameters that the Hodgkin-Huxley equation for how the voltage changes needs. So this is the transmembrane potential, the capacitance. This is the maximal conductance of sodium channels, maximal conductance of potassium channels, maximal conductance of a leakage channel. This is your reversal potential for sodium channels, and so on. And I'm also going to define an input current. So I want to have a way to stimulate my neuron in the ODE to give it a shock to set it off so I create an action potential. So I'm going to give a sinusoidal input here. This is my input with an amplitude I0. And I'm initially going to set I0 to 0 so that there is no input, so that my neuron doesn't keep firing. And later I'll turn this on and allow it to fire periodically. Then I specify a differential with respect to t, which is what I've done here. And I can set that my differential of V with respect to t is the Hodgkin-Huxley equation. So it's -1 over the membrane capacitance times the current from the potassium channel plus the current from the sodium channel plus a leakage current plus my injected current. And I create a Modeling Toolkit ODE system, and that's what I return up here. And I call it voltage ODE. And so here you can see the actual ODE that gets generated, which is the classical Hodgkin-Huxley equation for a neuron. So now I've got these 2 pieces. I've got my reaction system with my 6 reactions that tell me how my gating variables open and close. And I've got an ODE system for how my transmembrane potential changes. How do I combine them together? Well, I just take my reaction model and I extend it with the ODE model that I created. And that gives me a Hodgkin-Huxley model. So now I've composed the 2 together. I've combined them together, and we've added this ODE for the voltage in as a constraint to our Hodgkin-Huxley model. So now we've got a reaction system that internally has a coupled ODE system for the voltage, and we're ready to actually start simulating. So first, let's figure out the steady state so we can start our neuron at rest. So that's what I'm doing here. I'm picking a big time interval. I'm picking just a made-up initial condition, and I'm now solving the model out to a long time. And you see, I actually, even with my made-up initial condition, I get an action potential for the voltage. Notice I'm only plotting vars equals V, the symbolic variable for the voltage, the transmembrane potential. So here I get my action potential. And now if I take the value of this solution at the final time, that is the steady state resting value of my neuron. So it's the steady state value of V and M and H and so on. So I pull that out from the solution. I just take the solution at the very end. And now I've got for all my variables their steady state values. And I'm now going to turn back on my applied current. So I get that coefficient of the applied current. Remember, this was the amplitude of the applied current. I pull it out. I set it to be 10 now instead of 0. So I have a periodic sinusoidal current or sine squared current. I set my initial value to be the steady state I just pulled out. I solve my ODE problem. And now I get a whole series, a periodic series of action potentials firing with both the chemistry and the transmembrane potential being simulated via differential equations.jl. And so Catalyst has this kind of nice setup where you can kind of combine things together. It doesn't work for all models. So right now, you can't do this kind of composition to make jump process models with coupled ODEs. But that's where we're headed long term. And it certainly works with ODEs, and it may work with SDs. I haven't tested it too much yet. But if this is something that's of interest to you, we'd love issues if you play around with it and things work or don't work, if you let us know either way. Okay, and I think that was my very long section there. I'll turn it back over to Torkel to change gears and tell us about how we can do bifurcations in Catalyst now.
Yeah. Okay, I see if I can successfully add all of the streams and stuff. Do things seems to work? So really in this section, excellent. Two packages I want to show. One is a bifurcation kit, and the other one is called homotopy continuation. And these are two Julia packages, which I think we're like really lucky to have within the community, which allows us to do some really cool stuff. And they're both related to finding steady states of biochemical. Well, in this case, the steady state of biochemical reaction networks, but both also have wider application. So I'll start with bifurcation kit, which I'm going to here use to find bifurcation diagrams. But I also recommend to just check, search for bifurcation kit Julia, and you will see the package, and it can really do lots and lots of really fancy stuff. So in principle, what we have in bifurcation diagram, we want to track how the steady states of the system change with some parameter. So if you consider an ODE system, and if we were to simulate it for a long time, what typically happens is that we reach some steady state and the system rests there. And that's where all of the dx, dt, dy, dt, etc., is equal to 0. So the system does not change anymore. And bifurcation kit allows us to like find how does these steady states change with whatever parameter. And I'm going to use the same model as we used before for the simulation, so this positive feedback model. We previously saw that the model seems to have two different steady states, one for low X concentration and one for high. And we show that reaching this high steady state requires to change this parameter I, the input parameter. So what I now want to do is to find how does the steady states get affected by the value of this parameter I. So the first step, this is a little bit convoluted, but basically I need to transform this model into something which bifurcation kit can read. So bifurcation kit is not really part of the scientific machine learning ecosystem. However, I think specific support is being worked on. So hopefully in a couple of months you don't actually have to do this step. You can pretty much just call make bifurcation diagram with this kind of model. So first what we have to do is we have to convert to an ODE function from this model to something on the ODE form. We have to get an F function, so the actual ODE function, and a J function, which is the Jacobian. And then we'll get this jet thing, which will be the input to bifurcation kit. But this is, you can copy paste this and do this with whatever model here. You just plug it in there. You get out this jet, and you're going to use it in then. Next, we have to set the parameter values. So these are the parameter values for which we want to do the bifurcation diagram. Now, of course, one parameter here, I, is going to be changed. So the value here doesn't really matter, but the other one's going to be fixed. And here I'm just going to specify the index of the parameter which I want the bifurcation with respect to. In this case, I is the first parameter. And one thing I hope when I have like specific support for bifurcation kit in SciML is that you could just instead specify something like this. But now we are set first. and then a parameter span, which is the span over which we want to do bifurcation diagram. And here, when I plot my bifurcation diagram, I just want to say the concentration of which variable in the steady state do I want to plot. Here, of course, only one species, so the only real option is 1. And bifurcation kit also allows you to have function of the various states in the system. And then here, and I might go into why, but when we do the bifurcation diagram, we're going to start with this set here. So I want to change, so the value of the target parameter, in this case the first one, is also the value of the first in this span. So I create a copy of this parameter set, so not to modify it, and then I set the parameter 1 and the first parameter to be called the first in a parameter set, in a parameter spawn. And finally, I have to provide a guess for the initial conditions at the initial parameter set. So at this parameter set here. And this can be a very rough guess. I think this guess is not, I think this is off by an order of magnitude. But I have to write something. And then I write this continuation parameter object, which basically is the options to bifurcation kit. So it takes quite a few options, and I kind of bundle them up and provide them here. So p mean is going to be the value of, this is just the minimum parameter value, which is just this thing here. And p max is the maximum value in parameter span. Then we have ds max and ds mean, and which is basically like the stepping. So we're going to step in the bifurcation diagram for our p-value. And this is basically like what is the longest step we're going to make and what is the smallest step. And here I can select two arbitrary one. And then this ds is just going to be the initial step we're going to start with. And I usually, it's not too important, but usually select something in between these two. And the one important thing here is that I can have a minus here, and this kind of selects the direction. And if for some reason, say I want to start at this final point, so I want to set here we start at 1, and then we're going to go from 1 to 0, then I would have to have a minus sign here. But using this notebook here, I just say, okay, ds, there's going to be a positive number, and we're going from low to high value. And this detect bifurcation basically say, do we want to detect bifurcation points? And then I calculate my bifurcation diagram. There are several functions for doing this. The simplest one is just using this bifurcation diagram function. But there's some other ones for more advanced continuations. And I give my yet object, my unode object, my parameter values. This thing here basically says that I want to do it with respect to the first parameter. Remember, this is equal to 1. Here we have, this basically gives my output. This is some tangent algo. There's a few different ones. This one usually works. And record from solution basically says what we want to output. And here I want to just select my output vector at the plot variable. So just the concentration of 1. And this basically say I don't want to provide lots of output when I run it. And again, go to bifurcationkit.jl for more details. And in practice, there are tons and tons of consideration when running these bifurcation diagrams. So not always this default option is going to work, and you have to do some tuning. And I will show some basic things that you need to think about. But yeah, if you want to do the advanced one, just check that one. And you can do a lot of really cool stuff. Anyway, here we calculate the bifurcation diagram. And then we just plot it using plot, this output thing here. And here we see that the x concentration as a function of the parameter, in this case the input, between 0 and 1. And we see that we go from low concentration here to a high concentration here. So I have this bistable switch. We have a monostable inactive state. Here we have two stable steady state. And here we have a single one active. The bifurcation points here are marked. Here's the blue ones. This is fold bifurcation points, but we can detect other ones as well. And the stable steady states here are marked with a slightly thicker line, and the unstable one is the thin one. So here we have an unstable steady state, and here we have stable ones. Now, there's a few things I want to say here. Like, for example, one, here say that instead select the time span, the parameter span 0 to 0.2. So I only compute this part of the bifurcation diagram. I'm going to start in this point, and then I track left, and here I end. And we can see here that here we miss quite a lot. So this part is still part of the bifurcation diagram. But if you use this bifurcation diagram function to calculate it, you're just going to track from this initial point and continue. And this means that you won't be able to start find these joint trajectories. So I'm going to have like one example. And I'm going to see, I'm going to try and check the change which screen I show. So try to move that, add a stream. Right. Stop. I'm going to share a different one. Share. And let's see if this works. So say that we have a bifurcation diagram like this, where these two things doesn't connect. And if I then start in this point here, and work myself here, I will never be able to find this part of the bifurcation diagram. And there are, like, you can use deflated continuation and stuff to do this one as well. But here I just wanted to show the simple example. However, what we have in this case, we have something like this, and then we can find the entire thing. So I'm going to go back and share what was previously sharing. Okay. So this is like a thing that you need to think about. And this really to show that this is quite a complex software. Like, you can do basic ones like this. And if you want to do really cool stuff, you can like do bifurcation of spatial systems, for example. But then you really have to explore what the package can do. And it's really an amazing package. I can't recommend it enough. And then we have the second package, which is also an external package called homotopy continuation. And basically what homotopy continuation does, it's a package for solving a polynomial system. So say that you have a multivariate polynomial and then have a system of those. So for example, you have 3 polynomials in 3 different variables, and this lets you find the roots of them. So we all know that we have one polynomial in a single variable. We can find a limit to how number of solutions there are, and we can find all of them. And typically, just like finding the solutions to equations is quite a hard problem. So I've given you an arbitrary functions, just being certain to say like, oh yeah, I find all of the solutions to these equations. You can't just do it. But we're dealing with polynomials, we can do it. And using homotopy continuation, if we're dealing with multivariate polynomial systems with n polynomials with n variables, we can find all of the solution. And what is nice here that is, if we have ordinary differential equations generated from chemical reaction network models, these will almost always be polynomial systems, unless you like add some thing stuff. Even if you have, like, for example, Michaelis-Menten functions, that's going to give you a rational polynomial which can be reduced to a polynomial system. So if you can solve polynomial systems, you can find the steady state of chemical reaction networks. And this really homotopy continuation lets us do. So here I have like a model from a 2009 paper, and it's not particularly exciting, but what it is a model we have, it can be bistable. And that means that there are several steady states. And if we only have one steady state, of course, we can just run a simulation until we like find the steady state. But if we have several steady states, it's more difficult. So here what I do, I declare my model, I declare some parameter values. And again, here I won't go into too much detail, but if you want, you can just copy paste this for whatever system you have. So I convert to this, I create a nonlinear system. Here I kind of sub in the parameter values, so these parameter values. And then I kind of convert this into something which is a little bit easier for multiple continuation to see. And then I use this as polynomial, which is basically a symbolics function, which lets you consider like a set of symbolic expression as a real polynomial. So you can use polynomial methods, which include homotopy continuation. I run this and do homotopy continuation.solve on these equations. And then I use this thing here to say that I want to extract real solutions. So of course, we're going to find a lot of solutions. They're going to have imaginary part, which we're not very interested in when dealing with chemical reactions, because you can't have imaginary species concentration. And here we get 3 different solutions. So I have a system with 3 steady states, which is actually not trivial to find otherwise. But homotopy continuation lets us do this. And again, I really encourage you to check out the package. Your search homotopy continuation .gl Julia. You find the GitHub page and you can read all about it. And you have to do this thing. You can copy and paste this, and it will reliably always find the various steady states. Or I should note, in this case, it's fine, but sometimes here we filter out the imaginary solutions, but we're still going to have solutions which might have negative numbers. And of course, we need to filter away this as well, because you can't have negative concentrations. This is another 2 packages. And again, using these 2 packages, you can really find some cool stuff. And here, again, there's an exercise if people are interested. And then I think I will leave to Sam, who might have time to quickly go through the last part, I hope.
I do. Thank you. Perfect. I think it's just enough time. Okay, so in the last few minutes, I just wanted to tell you a bit about some of the network analysis functionality we have in Catalyst. And we have an enormous amount of this that's covered in the Catalyst tutorials. There's a network analysis tutorial. I just wanted to show you one piece. So the piece I'm going to show you is detection and elimination of conservation laws. But you can also calculate stoichiometry matrices and rate law vectors. You can calculate what are called linkage classes and deficiencies of networks, and whether networks are weakly reversible. So there's all kinds of things we've got built in, but there's not really time to go through it today. So let's talk a little bit about conservation laws. So if I have just the system A plus B reversibly goes to C, then probably everyone, or hopefully most of you, if we look at this, will say, I don't really have 3 independent variables here, because the amount of A's and B's are very related to the amount of C's. And in particular, if I know the amount of A and how much I had of everything initially, I can figure out the amount of B's and the amount of C's. That's called the conservation law. So dA dt will equal dB dt will equal minus dC dt for this system. So that's something we're going to exploit in a minute. So first, if I just take this system and I set some default values for my parameters and my initial conditions, and I convert it to a nonlinear system, I get this set of equations for the steady state. And you can already see there's a bit of an issue, because this is not a linearly independent set of equations. These are basically the same equation written 3 times. So if I want to solve for steady states, I'm going to end up from this equation getting an infinite set of solutions. I'm not going to get a specific solution. And that's a problem. And we can try it. Suppose we load homotopy continuation and do what Torkel just showed us. We'll get an error that homotopy continuation can't calculate a steady state for this system. Okay. And the problem is because there's an infinite set of steady states because of the conservation law that's hidden in here. So what we can do with Catalyst is we can actually calculate the conservation laws and remove those variables, reduce the size of the system, so that now we get a single equation for one of the variables, A, B, or C, that can be solved. And that's what I just wanted to show you very quickly. So just calling the conservation laws command on our reaction network goes and internally calculates all the conservation laws of the system. So here we get out a matrix that says, this is A, this is B, this is C. So one conservation law is that minus A plus B is a constant. this tells us the other conservation law is that A plus C is a constant. If we call conserved equations, we can actually see variables that Catalyst will eliminate to get rid of those redundant steady state equations. So here it's telling us that it can eliminate B by saying B is A plus the constant for the first conservation law, and C is the constant for the second conservation law minus A. And what are those constants? Well, those constants, if we look at conservation law constants, they're just the amount of B minus the amount of A and the amount of A plus the amount of C. And how can we calculate them? Since they're constants, we can just calculate them at time 0 and then know what they are. So let's do that. So now I convert my reaction system to a nonlinear system, and I tell it, remove the conservation laws. So what it's going to do is internally, when it's creating the nonlinear equations, it's going to eliminate B and C. And it's just going to give me an equation for A. And that's exactly what we see here. We get one equation. 0 is K minus times this times this times this. This is just the equation for A in terms of my two conservation law constants. And those constants can be calculated from the initial condition. Now we can go and do what Torkel just showed us on the new system where we just have one equation. We can run homotopy continuation and it tells us the steady state. So it spits it out. And just to show you that this is all self-consistent, here I've gone and I've solved the original system to steady state and plotted A. And then I put on at the end the steady state that homotopy continuation gave us. And sure enough, that's what A is converging to. You might be worried, well, wait, if we eliminated B and C, what if in my simulations I need to use B? Maybe I want to measure B squared or something. That's an important observable of the system. Well, conveniently, Catalyst and Modeling Toolkit doesn't throw them away. It just makes them not be state variables anymore. They're converted into what's called observables, and you can still access them in the same way. So if I wanted to say plot the amount of B, I can take my system and unpack the symbolic B variable and the symbolic C variable, and I can say plot those B and C variables. So even though they're no longer unknowns of the system, they're now getting plotted, and I can evaluate them and get their values. And then here I've just plotted B plus C. So here I evaluated the solution at a bunch of times, the solution for B at a bunch of times, and the solution for C at a bunch of times, and I added them up. And I'm plotting it just to show you that they really are constant. That really was a conservation law. So this is another nice feature that Catalyst has. If you have a reaction network where you have conserved variables or species, when you convert to ODEs, the Jacobian of the system will be singular. At steady state, you'll generally get a singular, you'll get a set of equations that are not linearly independent, and that will cause problems trying to solve for steady states or trying to do calculations involving the Jacobian. So by using this remove conserved keyword, Catalyst will calculate the conservation laws, move them out of the system so that everything becomes much more nicely defined and works better in these other higher level applications. But it doesn't throw away those variables. You can still calculate and evaluate them in case you need that for your own application. And I know that was kind of quick, but the notebooks are all posted at the link that we gave at the start of the presentation. Just go to the Catalyst.jl website, and it's linked there right now. So you can look at these notebooks and Torkel's notebooks. And that was actually everything I had. So let me bring Torkel back on. You added yourself and I removed you. But I just wanted to say thank you to all for coming. Thank you, Torkel, for helping run this. Hope this was helpful and of use to some of you. If you have questions, you can post them now on the Pigeonhole site. Unfortunately, I can't access the Discord. So if anyone has asked questions on the Discord, for some reason, Discord is locked to me. But if you have a question, maybe Torkel can figure out how to go on there. Or otherwise,
I'm quickly making an attempt to go to the Discord.
Yeah. Or otherwise, please feel free to post on SciML Bridged or DiffyQ Bridged on Slack or on Zulip, or open an issue on Catalyst. We watch all those channels, and we're happy to hear from you. And if you have questions, if you want to know how to do something, if there's functionality we're missing that you think we should have. Someone asked about spatial. So you don't need to ask, are we planning spatial? Yes. In fact, we have some grants that are funding us to work towards spatial. That's something that I'm hopefully in the fall going to be working on. So hopefully we'll have some spatial modeling functionality within 6 months to a year. But yeah, And otherwise, I think we can stop it there. If you have questions, feel free to ask them. If we see them, we'll answer them in the next couple minutes. And otherwise, we'll end the stream right at 5 on time. So,
Yeah.
I don't know. Were you able to get in, Torkel? I don't
I'm
know
still
why I'm
working.
locked out. So,
Yeah.
okay. Well. Yeah, Frank Chen, if you want to contact me, you can message me on Slack, the Julia Slack, or you can email me. If you just Google my name, Samuel Isaacson, my email is on my website. So, but all right, I think we should probably, why don't we end the stream there? So thanks again, Torkel. Thank you all for coming.
Thanks, everyone.
Have a good rest of the day wherever you're located. So.